From Earth, the night sky looks scattered, stars appear isolated, galaxies seem separated by enormous empty space. But on the largest scales, the universe is not random. It is organized into vast rivers of galaxies, flowing along invisible gravitational currents. These rivers form structures so large that individual galaxies become insignificant points inside them. One of these structures is called Laniakea, a supercluster containing more than 100,000 galaxies stretching across hundreds of millions of light years and slowly pulling everything inside it toward a common gravitational destination, including us. The Milky Way is not drifting through space alone. It is part of this enormous cosmic flow, moving at hundreds of kilometers per second through intergalactic space, guided by gravitational forces we cannot see. In this documentary, we will trace the true shape of the Laniakea Supercluster. We will follow the motion of galaxies, map invisible filaments of dark matter, and explore how gravity organizes the universe on the largest possible scales. We will see where Laniakea begins, where it ends, and what lies beyond its boundaries. If you enjoy deep space documentaries that reveal the hidden structure of the cosmos, consider subscribing, because once you understand where we really are in the universe, the night sky never looks the same again. The story of Laniakea does not begin with galaxies, it begins with gravity itself. On the largest scales, gravity is the architect of structure. It does not build with solid walls or visible boundaries. Instead, it shapes the universe through slow, persistent attraction. Over billions of years, tiny differences in density grow into enormous cosmic patterns. These patterns eventually become the vast networks of matter we now call the cosmic web. In the earliest moments after the Big Bang, the universe was nearly uniform. Matter was spread out almost evenly, with only minute variations in density. These small irregularities were not random noise. They were the seeds of everything that would follow. Where matter was slightly denser, gravity pulled more material inward. Where it was slightly less dense, matter slowly drained away. Over time, this process amplified itself. Dense regions became denser, empty regions became emptier. This gradual amplification gave rise to the large-scale structure of the universe. Instead of forming evenly distributed clouds of galaxies, matter organized itself into filaments, sheets and nodes. These structures stretch across hundreds of millions of light years, creating a vast interconnected network. Galaxies form along these filaments, gathering at intersections where gravity is strongest. This network is known as the cosmic web. Within the cosmic web, smaller structures exist inside larger ones. Individual stars form galaxies. Galaxies group into clusters. Clusters gather into superclusters. And superclusters connect into enormous flows of matter moving across intergalactic space. Laniakea is one of these massive gravitational domains. Its name comes from Hawaiian, meaning immense heaven or unmeasurable sky. The name reflects both its scale and its significance. Laniakea is not a simple cluster of galaxies, it is a region of space where galaxies share a common gravitational destiny. The Milky Way is part of this region. This means that our galaxy is not drifting randomly through space, it is moving along a gravitational flow that spans hundreds of millions of light years. To understand how Laniakea formed, scientists had to move beyond traditional methods of mapping space. For decades, astronomers classified cosmic structures by grouping galaxies based on proximity. If galaxies appeared close together, they were placed in the same cluster or supercluster. This approach worked well for smaller scales, but became less effective when dealing with enormous regions like Laniakea. Superclusters are not tightly bound objects like galaxies or clusters. They are loose, extended structures defined more by motion than by physical attachment. What defines Laniakea is not simply where galaxies are located, it is where they are going. Galaxies are not static, they move through space under the influence of gravity. These motions create large-scale flows that reveal the underlying structure of the cosmic web. To trace these flows, astronomers measure something called peculiar velocity. Peculiar velocity is the motion of a galaxy relative to the overall expansion of the universe. While the universe is expanding and pushing galaxies apart, gravity pulls some galaxies toward massive regions. The difference between these motions reveals the direction of gravitational influence. By measuring the peculiar velocities of thousands of galaxies, scientists can map how matter is flowing through space. When this data was combined and visualized, a remarkable pattern emerged. Galaxies across a vast region were found to be moving toward a common gravitational basin. This basin lies near a region known as the Great Attractor, a massive concentration of matter hidden behind dense clouds of interstellar dust that obscure direct observation. This gravitational convergence defined the boundaries of Laniakea. Rather than being defined by walls or edges, Laniakea is defined by flow lines. If a galaxy's motion carries it toward the same gravitational center, it belongs to Laniakea. If its motion points elsewhere, it belongs to a different supercluster domain. This approach revealed something profound. The universe is not just divided by distance, it is divided by gravitational influence. Laniakea stretches across roughly 520 million light-years and contains over 100,000 galaxies. Within this region, matter is slowly flowing inward toward massive structures that dominate the gravitational landscape. Our Milky Way is part of this flow. We are moving at hundreds of kilometers per second relative to the cosmic background, carried along by gravitational currents shaped over billions of years. This motion is not dramatic on human timescales. It is slow and imperceptible. But over cosmic time, it defines the large-scale architecture of matter. The formation of Laniakea reflects the interplay between expansion and gravity. The universe expands, pulling everything apart. But gravity resists expansion locally. Where enough matter accumulates, gravitational attraction overcomes expansion and binds structures together. On the scale of galaxies and clusters, gravity dominates. On the scale of superclusters, gravity competes with expansion. Laniakea exists at this delicate boundary. It is not gravitationally bound in the same way a galaxy cluster is. It will not collapse into a single object. Instead, it represents a long-lived flow structure shaped by the balance of cosmic forces. This makes superclusters fundamentally different from smaller cosmic objects. They are not solid entities. They are dynamic regions. Their shapes evolve over time, their boundaries shift. Their internal flows change as matter redistributes itself. Laniakea is not a permanent structure. It is a snapshot of the universe in motion. Understanding this motion requires mapping not only where galaxies are, but how they move through space. This is one of the greatest technical challenges in cosmology. Distances across hundreds of millions of light-years must be measured with extreme precision. Velocities must be separated from expansion effects. Errors must be minimized across enormous data sets. Despite these challenges, the picture that emerges is remarkably consistent. Galaxies move along filamentary highways of dark matter. These invisible structures dominate the mass of the universe and shape the visible distribution of galaxies. Dark matter does not emit light, but its gravitational influence sculpts the cosmic web. Without dark matter, superclusters like Laniakea would not exist in their observed form. It is the hidden scaffolding of the universe. Laniakea is built on this invisible framework. The Milky Way sits along one of these filaments, slowly drifting towards denser regions of matter. This journey will take billions of years and will never reach a final destination in the traditional sense. The flow is part of a larger, ongoing redistribution of matter across cosmic scales. This perspective changes how we think about location. We often imagine our galaxy as stationary, surrounded by distant objects. In reality, everything is moving. The Earth moves around the Sun. The Sun moves within the Milky Way. The Milky Way moves within the local group. The local group moves within Laniakea, and Laniakea itself moves relative to even larger cosmic structures. There is no absolute rest frame. There is only motion layered upon motion. 1. This hierarchy of movement reveals the nested structure of the universe. Small systems exist within larger ones, each shaped by gravitational influence from above and below. Laniakea is one of the largest known examples of this nesting. It contains smaller clusters such as the Virgo cluster, which plays a central role in our local cosmic neighborhood. The Virgo cluster acts as a gravitational anchor within Laniakea, drawing nearby galaxies inward. This inward flow is not smooth. It is turbulent on large scales. Matter streams along filaments, colliding at intersections, forming massive clusters. These collisions generate shock waves, heat intergalactic gas, and shape the evolution of galaxies. The formation of superclusters like Laniakea is therefore not a quiet process. It is dynamic and energetic. Over billions of years, matter is constantly rearranged by gravitational forces. Structures grow, merge, and evolve. Yet despite this constant motion, the overall pattern of the cosmic web remains stable on large scales. Filaments persist. Voids remain empty. Clusters continue to grow. Laniakea exists within this larger pattern. It is not isolated. It connects to neighboring superclusters through filaments of matter. These connections form bridges between massive structures, creating an even larger cosmic network. Beyond Laniakea lie other superclusters, each with its own gravitational flows and boundaries. Together they form the largest known patterns in the observable universe. Understanding Laniakea is therefore not just about mapping one structure, it is about understanding how the universe organizes itself on the grandest scales. It reveals that the universe is not random, it is structured. It is dynamic. It is shaped by invisible forces acting over unimaginable distances. And within this structure, our galaxy occupies a specific place. Not central, not unique, but connected. We are part of a vast gravitational story that began shortly after the Big Bang and continues to unfold today. In the next part, we will examine the tools scientists use to trace these invisible flows, how velocity maps are created, and how astronomers turn raw data into three-dimensional maps of the universe's hidden architecture. Because seeing Laniakea is not about looking through a telescope, it is about learning how to read the motion of the cosmos itself. Mapping Laniakea is not like drawing the outline of a continent on Earth. There are no coastlines, no sharp borders, no visible edges. Instead, scientists must reconstruct its shape by tracking invisible gravitational currents that guide the motion of galaxies across enormous distances. To do this, astronomers rely on a combination of distance measurements, velocity data, and statistical reconstruction techniques. Together, these tools allow researchers to transform scattered observations into a coherent picture of the cosmic landscape. The first challenge is measuring distance. On Earth, distance can be measured directly using rulers, radar, or GPS. In space, such methods are impossible. Instead, astronomers use indirect indicators known as cosmic distance ladders. Some galaxies contain objects with predictable brightness, such as certain types of supernovae and variable stars. By comparing how bright these objects appear to how bright they are known to be, these measurements are difficult and prone to uncertainty. Small errors become enormous when distances stretch across hundreds of millions of light years. Yet precision is essential because accurate distance estimates allow astronomers to separate two key effects: cosmic expansion and local motion. The universe is expanding, causing distant galaxies to appear to move away from us. This motion follows a predictable pattern known as the Hubble flow. But galaxies also experience additional motion caused by gravitational attraction from nearby mass concentrations. This additional motion is called peculiar velocity. Peculiar velocity reveals the direction and strength of gravitational influence. If a galaxy is moving faster toward a region than expansion alone would predict, it indicates the presence of unseen mass pulling it inward. By measuring these deviations from the expected expansion rate, scientists can trace the invisible structure of gravity itself. This process requires gathering data from thousands of galaxies, Each measurement adds a small piece to the puzzle. When combined, these pieces reveal large-scale flow patterns across space. To visualize these flows, astronomers use computational techniques that reconstruct the three-dimensional velocity field of the universe. This field shows how matter moves through space over cosmic distances. When these reconstructions were applied to our local region of the universe, a striking pattern emerged. Galaxies were not moving randomly. They were flowing along curved paths toward a central gravitational basin. This basin lies in the direction of the Great Attractor, a massive concentration of matter obscured by dust and gas in the plane of the Milky Way. Although the Great Attractor itself is difficult to observe directly, its gravitational influence is unmistakable. Thousands of galaxies are being pulled toward this region. This flow defines the heart of Laniakea. By tracing which galaxies share this inward motion, scientists were able to identify the boundaries of the supercluster. These boundaries are not defined by empty space. They are defined by divergence points in gravitational flow. At certain locations, galaxy motion splits. Some galaxies flow toward Laniakea's core, while others flow toward neighboring superclusters. These dividing lines form the natural borders between cosmic regions. This method is similar to mapping watersheds on Earth. Rain falling on one side of a mountain ridge flows towards one river system. Rain falling on the other side flows elsewhere. The ridge defines the boundary between drainage basins. In space, gravity replaces water. Galaxies flow along gravitational gradients. The boundaries between superclusters are cosmic watershed lines. Laniakea is one such gravitational basin. Understanding this flow-based structure requires precise modelling. Astronomers must account for the distribution of visible matter, dark matter, and the effects of cosmic expansion. They must also correct for observational biases, incomplete data, and distortions caused by redshift measurements. Despite these challenges, the reconstructed maps show remarkable coherence. Filaments extend outward from Laniakea, connecting it to neighbouring superclusters such as Perseus Pisces and Coma. These filaments act as highways of matter, channeling galaxies and gas across enormous distances. This interconnected network forms the backbone of the cosmic web. Within this network, Laniakea occupies a prominent position. It is not the largest supercluster in the observable universe, but it is one of the most significant in our local cosmic neighbourhood. Its scale is difficult to comprehend. If the Milky Way were reduced to the size of a grain of sand, Laniakea would span the size of a continent. Yet this immense structure is invisible to the naked eye. We do not see Laniakea directly. We infer it from motion, gravity, and subtle distortions in the distribution of galaxies. This highlights an important truth about modern cosmology. Much of the universe is not observed directly. It is reconstructed. This reconstruction is not guesswork. It is grounded in physical law and validated by multiple independent observations. But it requires interpretation and modelling. Laniakea exists not as a bright object in the sky, but as a pattern in data. This pattern reveals something profound. The universe organizes itself through motion. Structure is not static. It emerges from dynamic processes. Galaxies move, clusters evolve, superclusters shift. The cosmic web is alive with motion, even though this motion unfolds over billions of years. Laniakea's shape reflects this dynamic nature. Its boundaries are not rigid. They evolve as matter redistributes itself and gravitational influences change. Over cosmic time, superclusters can merge, fragment, or be reshaped by expansion and dark energy. This means that Laniakea is not permanent, it is a transitional structure. It represents the current arrangement of matter in our region of the universe. In the far future, expansion driven by dark energy will weaken the gravitational connections between distant parts of Laniakea. Some regions may drift apart, becoming causally isolated. The supercluster we observe today will not look the same billions of years from now. This highlights the tension between gravity and expansion. Gravity pulls matter together. Expansion pushes space apart. Superclusters like Laniakea exist at the boundary where these two forces compete. This competition creates temporary large-scale structures that persist for billions of years but are ultimately shaped by the accelerating expansion of the universe. Understanding this balance is essential to understanding cosmic architecture. It explains why the universe does not collapse into a single massive structure. It also explains why matter does not remain evenly distributed. The interplay of forces creates a dynamic equilibrium that generates complexity. Another important aspect of mapping Laniakea involves accounting for dark matter. Dark matter makes up most of the mass in the universe, yet it does not emit or absorb light. Its presence is inferred from gravitational effects on visible matter and radiation. When scientists map gravitational flows, they are effectively mapping dark matter distribution. Laniakea's structure is therefore dominated by invisible mass. The luminous galaxies we see are only tracers embedded within a much larger dark framework. This means that the true shape of Laniakea is far larger and more massive than what is visible through telescopes. It is a shadow of something much bigger. This realization transforms how we think about cosmic structure. The visible universe is only a surface layer. Beneath it lies a hidden architecture that governs motion and evolution. Laniakea is one manifestation of this hidden structure. Another challenge in mapping superclusters is dealing with cosmic voids. Voids are vast regions of space with very little matter. They can span tens to hundreds of millions of light years. These empty regions play a crucial role in shaping cosmic flows. Matter tends to flow away from voids and toward dense regions. This movement reinforces the filamentary structure of the cosmic web. Laniakea is surrounded by voids that help define its shape and boundaries. These voids are not completely empty. They contain faint gas and dark matter, but their low density makes them gravitationally pulsive in effect. Not because they push matter away directly, but because matter is drawn more strongly toward denser regions. This creates a pattern of evacuation from voids and accumulation along filaments. Mapping these voids is just as important as mapping clusters. Together, they define the full geometry of Laniakea. This process reveals the universe as a landscape of peaks and valleys in gravitational potential. Dense clusters form deep gravitational wells. Voids form high gravitational plateaus. Galaxies roll downhill along these gradients, shaping the cosmic web. Laniakea is one of the largest valleys in our region of space. The Milky Way is currently moving along one of the slopes leading into this valley. This motion is slow but persistent. Over billions of years, our galaxy's position relative to the rest of Laniakea will change, even as local structures such as the local group remain gravitationally bound. This perspective reveals that location in the universe is not static, it is a snapshot of motion. We exist at a particular moment in a long gravitational journey. Mapping Laniakea allows scientists to reconstruct that journey. It shows where matter has been flowing. It suggests where it is headed. It reveals the invisible currents shaping the universe. In the next part, we will examine the interior of Laniakea itself, the massive clusters that anchor its gravitational structure, the role of the Virgo cluster, and how these dense regions dominate the flow of galaxies across hundreds of millions of light years. Because to understand the edge of Laniakea, we must first understand its core. At the heart of Laniakea lies a complex network of massive galaxy clusters that act as gravitational anchors. These dense regions do not merely contain large numbers of galaxies. They shape the motion of matter across vast distances, pulling surrounding structures into coherent flows. To understand Laniakea as a whole, it is necessary to examine these internal gravitational centers and the roles they play in organizing the supercluster. One of the most important of these centers is the Virgo cluster. The Virgo cluster is the nearest major galaxy cluster to the Milky Way and serves as the central hub of our local cosmic neighborhood. It contains thousands of galaxies packed into a relatively compact region of space. This concentration of mass creates a deep gravitational well that influences the motion of nearby galaxies, including our own. The Milky Way, along with its neighbouring galaxies in the local group, is slowly moving toward Virgo. This motion is subtle, unfolding over hundreds of millions of years, but it is measurable. It reflects the gravitational pull exerted by the cluster's enormous mass. Virgo is not alone. Within Laniakea, several major clusters and groups form a distributed network of gravitational centers. Each contributes to the overall flow pattern. Some clusters act as intermediate gathering points, collecting matter from surrounding filaments before passing it along toward larger concentrations. This hierarchical structure is typical of the cosmic web. Small groups feed into larger clusters. Clusters feed into superclusters. Superclusters connect through filaments into even larger networks. Laniakea is one layer in this nested hierarchy. The distribution of mass within Laniakea is not uniform. Some regions are dense with galaxies and dark matter. Others are relatively sparse. This uneven distribution creates complex gravitational landscapes that guide galaxy motion. Matter does not fall directly inward along straight lines. It follows curved trajectories shaped by multiple gravitational influences. This results in swirling flow patterns that resemble rivers merging into larger basins. These flows are not chaotic, they follow predictable paths determined by the distribution of mass. Over cosmic time, these paths remain stable even as individual galaxies move along them. The stability of these flows allows astronomers to reconstruct the structure of Laniakea with increasing accuracy. One of the most intriguing features of Laniakea's interior is the presence of the Great Attractor region. This region represents a massive concentration of matter located in the direction of the Norma cluster. The Great Attractor exerts a strong gravitational pull on surrounding galaxies, including many within Laniakea. Despite its importance, the Great Attractor is difficult to observe directly. It lies behind dense clouds of dust and gas in the plane of the Milky Way, which block visible light from distant galaxies. This region of obscured sky is known as the Zone of Avoidance. To study this hidden area, astronomers rely on alternative wavelengths such as infrared and radio observations, which can penetrate dust more effectively. They also infer the presence of mass by observing galaxy motions in surrounding regions. These methods reveal that the Great Attractor is not a single object, but part of a larger complex of massive clusters and filaments. It represents one of the deepest gravitational wells within Laniakea. Galaxies across hundreds of millions of light years are slowly drifting toward this region. This inward motion contributes significantly to the overall flow pattern of the supercluster. However, Laniakea is not dominated by a single central point. It is shaped by multiple gravitational centers working together. This distributed structure makes Laniakea fundamentally different from simpler cosmic systems. It does not have a core in the traditional sense. Instead, it has a gravitational center of influence defined by the combined mass of several clusters and filaments. This makes its internal dynamics complex and rich. The presence of multiple gravitational anchors also means that different parts of Laniakea experience different evolutionary pressures. Regions closer to dense clusters undergo more frequent galaxy interactions and mergers. Gas is heated by gravitational compression. Star formation rates can be influenced by these energetic environments. In contrast, regions located along filaments or near voids experience lower interaction rates. Galaxies in these areas evolve more quietly, with slower rates of merging and more gradual star formation histories. This diversity of environments within Laniakea creates a wide range of galactic conditions. The supercluster is not uniform. It contains extremes of density, temperature, and activity. Understanding this internal diversity is crucial for studying galaxy evolution. It shows that a galaxy's fate is not determined solely by its own properties. It is shaped by its cosmic neighborhood. The location of a galaxy within Laniakea influences how it evolves over billions of years. This environmental influence extends beyond visible matter. Dark matter plays an even larger role. The gravitational anchors within Laniakea are dominated by dark matter halos that surround clusters and filaments. These halos provide most of the gravitational mass that shapes galaxy motion. The visible galaxies are embedded within these halos like beads on invisible strings. This means that the true structure of Laniakea is largely hidden from direct observation. What we see is only the luminous outline of a much larger gravitational framework. Mapping this framework requires combining observational data with theoretical models of structure formation. Simulations of cosmic evolution show that superclusters like Laniakea emerge naturally from the growth of dark matter fluctuations in the early universe. Small density variations grow into filaments and nodes as gravity pulls matter together. Over time, these structures merge and evolve, creating the large-scale architecture we observe today. Laniakea is therefore not an anomaly, it is a natural outcome of cosmic evolution. Its specific shape and location reflect the initial conditions of the universe and the subsequent influence of gravity and expansion. Another important feature of Laniakea's interior is the presence of cosmic voids. Voids are large regions with low matter density. They surround filaments and clusters, creating a foam-like structure in the cosmic web. Within Laniakea, voids help define the boundaries of dense regions and guide the flow of matter. Matter flows away from voids and toward clusters. This movement reinforces the filamentary structure of the supercluster. Voids also play a role in shaping galaxy evolution. Galaxies located near voids tend to be more isolated and experience fewer interactions. They often retain their gas for longer periods and show different star formation patterns compared to galaxies in dense clusters. This environmental variation within Laniakea creates a complex mosaic of galactic histories. Some galaxies are shaped by repeated mergers and gravitational encounters. Others evolve quietly in relative isolation. This diversity is a hallmark of large-scale cosmic structure. It shows that the universe does not evolve uniformly. It evolves differently in different environments. The internal structure of Laniakea also reveals how cosmic flows change over time. As clusters grow more massive, their gravitational influence increases. This can alter flow patterns, redirecting matter from one region to another. These changes occur slowly, but they accumulate over billions of years. This dynamic evolution means that Laniakea's current shape is temporary. In the distant future, expansion driven by dark energy will weaken the gravitational connections between distant parts of the supercluster. Some regions may become isolated from others. Filaments may thin, flows may slow. The supercluster may fragment into smaller gravitationally bound units. This future evolution highlights the transient nature of large-scale cosmic structures. They exist in a balance between gravity and expansion. As expansion accelerates, this balance shifts. Understanding this shift is essential for predicting the long-term fate of superclusters. Another aspect of Laniakea's interior is the role of intergalactic gas. Between galaxies lies a vast reservoir of hot, diffuse gas known as the intracluster and intergalactic medium. This gas traces the gravitational potential of clusters and filaments. It emits faint X-rays and interacts with galaxies moving through it. As galaxies fall into clusters, they pass through this gas and experience ram pressure stripping, which can remove gas from their disks and suppress star formation. This process influences galaxy evolution within Laniakea. Dense environments shape not only galaxy motion, but also their internal structure and star-forming activity. This further emphasizes the interconnected nature of cosmic structure. Laniakea is not just a collection of galaxies. It is a dynamic ecosystem of matter, energy, and gravity. Every component influences the others. Clusters shape flows. Flows shape galaxy evolution. Voids shape structure. Dark matter shapes everything. This complexity makes Laniakea a powerful laboratory for studying large-scale structure formation. By examining its internal dynamics, scientists gain insight into the fundamental processes that shape the universe. They learn how matter organizes itself. They test models of dark matter and dark energy. They refine theories of cosmic evolution. Laniakea is therefore more than a map feature, it is a window into the mechanics of the cosmos. In the next part we will step outward and examine the edges of Laniakea itself, how astronomers determine where the supercluster ends, how it connects to neighbouring structures, and what happens at the boundaries where gravitational influence shifts from one cosmic basin to another. Because understanding the heart of Laniakea is only the beginning. To trace its true edge, we must follow the flow of galaxies all the way to the limits of its gravitational reach. Tracing the edge of Laniakea is not about finding a physical boundary in space. There are no walls, no sudden drop-offs, no visible markers that announce where the supercluster ends. Instead, the edge is defined by a subtle shift in gravitational influence, a transition zone where the flow of galaxies changes direction and cosmic currents diverge toward different destinations. This makes the boundary of Laniakea one of the most complex features in large-scale cosmology. Unlike galaxies or clusters, which can be outlined by brightness and density, superclusters exist as dynamic regions shaped by motion. Their edges are not static lines drawn on a map. They are fluid zones that evolve as matter redistributes itself across the cosmic web. To locate these boundaries, astronomers return to the same principle that revealed Laniakea in the first place: velocity flow. When the motion of galaxies is mapped across space, a pattern of convergence and divergence becomes visible. In some regions, galaxies stream inward toward Laniakea's gravitational basin. In others, they drift away toward neighbouring superclusters. The edge of Laniakea lies along these dividing lines. These boundaries are sometimes called cosmic watershed surfaces. Just as rainwater falling on different sides of a mountain ridge flows into separate river systems, galaxies located on opposite sides of a gravitational ridge flow toward different supercluster centers. This analogy is not poetic, it is physically accurate. Gravity creates potential gradients across space. Matter moves along these gradients. Where gradients intersect, boundaries form. Laniakea's edge is therefore a three-dimensional surface that curves through space, separating gravitational basins. This surface is not smooth, it twists and folds around filaments, voids and clusters. It adapts to the uneven distribution of matter. It changes shape slowly over time as mass accumulates or disperses. Mapping this surface requires enormous datasets and advanced computational tools. Astronomers combine velocity measurements, galaxy positions, and theoretical models to reconstruct the underlying gravitational field. From this field, the flow lines of matter can be traced. Where flow lines diverge, the boundary emerges. This process reveals that Laniakea is not isolated. It is embedded within a larger network of superclusters. On one side of Laniakea lies the Perseus-Pisces supercluster, a massive filamentary structure stretching across hundreds of millions of light-years. On another side lies the Shapley supercluster, one of the most massive concentrations of matter in the nearby universe. These neighbouring giants exert their own gravitational influence, pulling matter toward them and shaping the edges of Laniakea. The boundaries between these regions are not empty. They are zones of competition. In these transition areas, gravitational forces from different superclusters overlap. Galaxies in these regions may experience complex motions influenced by multiple massive structures. Some galaxies drift along curved paths, slowly changing direction as they respond to shifting gravitational dominance. This creates regions of cosmic tension where matter is pulled in different directions simultaneously. Over time, one influence may dominate, and the galaxy will settle into a particular flow basin. This process can take billions of years. The existence of these transition zones reveals how interconnected the cosmic web truly is. Superclusters do not exist as isolated islands. They are nodes in a vast network of gravitational relationships. Each one influences its neighbours. Each one competes for matter. Each one shapes the motion of galaxies across enormous distances. Laniakea's edge is therefore not a place where structure ends. It is a place where influence changes hands. This distinction is important. It means that the cosmic web is continuous, even though individual superclusters can be defined. There is no break in reality at the boundary, only a shift in gravitational direction. This continuity explains why filaments often cross supercluster boundaries. Filaments act as bridges between massive regions, channeling matter across different gravitational domains. Some filaments feed multiple superclusters, branching like river deltas across space. These structures blur the notion of sharp boundaries. They show that cosmic organization is hierarchical and overlapping. The edges of Laniakea are also shaped by cosmic voids. Large voids surround parts of the supercluster, creating natural barriers that redirect matter flow. These voids act as regions of low gravitational attraction, effectively pushing matter toward denser structures on their edges. In this way, voids help sculpt the shape of Laniakea. They carve out its contours. They define where filaments form. They influence where boundaries settle. This makes voids just as important as clusters in shaping supercluster geometry. Understanding the edge of Laniakea, therefore, requires understanding the balance between dense and empty regions. This balance is not accidental. It is the outcome of billions of years of gravitational evolution. Small density fluctuations in the early universe grew into the large voids and dense clusters we see today. These structures now define the flow patterns that outline superclusters. Another important factor shaping Laniakea's boundary is dark energy. As the universe expands at an accelerating rate, the influence of gravity weakens on the largest scales. This expansion stretches the cosmic web, gradually increasing the separation between distant structures. Over time, this effect will alter the shape of superclusters. Some filaments connecting Laniakea to neighboring regions will thin and eventually break. Flow patterns will change. Boundaries will become more defined as regions become causally isolated. This means that the current edge of Laniakea is not permanent. It is a snapshot in an ongoing process. In the far future, Laniakea may fragment into smaller gravitationally bound groups as expansion overcomes large-scale gravitational connections. This future evolution adds another layer of complexity to defining supercluster boundaries. They are not fixed features. They evolve. They respond to cosmic expansion. They adapt to changing mass distributions. This dynamic nature challenges the idea of static cosmic maps. Any map of Laniakea is time-dependent. It represents the universe at a particular moment. Understanding this helps avoid the misconception that superclusters are rigid structures. They are patterns of motion, not solid objects. This perspective also reshapes how cosmic scale is interpreted. When people imagine the universe, they often think in terms of size alone. But scale is not just about distance. It is about influence. The edge of Laniakea marks the limit of gravitational influence for this region. Beyond it, other superclusters dominate. This makes gravitational influence a more meaningful measure of cosmic structure than simple proximity. Two galaxies can be relatively close in distance but belong to different gravitational domains. What matters is not how far apart they are, it is where gravity pulls them. This redefinition of cosmic boundaries is one of the most important conceptual shifts in modern cosmology. It moves the focus from static position to dynamic motion. It shows that the universe is organized by flow rather than by fixed partitions. Another consequence of this flow-based structure is that the Milky Way's location within Laniakea is not permanent. Over billions of years, our galaxy's relative position within the supercluster will change. Local interactions, cluster mergers, and large-scale flows will alter its trajectory. However, the local group of galaxies, including the Milky Way and Andromeda, is gravitationally bound. This local system will remain intact, even as larger-scale structures evolve. This nested stability illustrates the layered nature of cosmic structure. Small-scale systems are more tightly bound, large-scale systems are more fragile. Laniakea exists in this fragile regime. It is stable over billions of years but not eternal. The edges of Laniakea also reveal something about the limits of observation. Superclusters extend across distances so large that mapping them requires combining data from many telescopes, surveys, and wavelengths. Some regions of the sky are obscured by dust in our own galaxy, others are too faint to detect easily. This means that our map of Laniakea is incomplete. There may be hidden structures, unseen filaments, and undiscovered clusters influencing the flow patterns. As observational technology improves, these hidden components may be revealed. Infrared surveys, radio telescopes, and future space missions will allow astronomers to peer deeper into obscured regions and refine the boundaries of Laniakea. This ongoing refinement highlights another important truth. Our understanding of cosmic structure is evolving. Laniakea itself was only identified as a distinct supercluster in the early 21st century. Before that, the Milky Way's place in the universe was understood differently. Future discoveries may further reshape this picture. New data may reveal that Laniakea is part of an even larger gravitational domain, or that its boundaries are more complex than currently believed. This uncertainty is not a weakness, it is a reflection of the scale and complexity of the universe. Mapping structures that span hundreds of millions of light years is an extraordinary scientific challenge. Every improvement in data brings new clarity and new questions. The edge of Laniakea therefore represents more than a physical boundary. It represents the frontier of cosmic mapping. It marks the limit of our current understanding of large-scale structure. Beyond it lie other superclusters, other gravitational basins, and other cosmic flows that we are only beginning to chart. Tracing this edge reveals the universe as a vast, interconnected network rather than a collection of isolated objects. It shows that even on the largest scales, structure emerges from simple physical principles. Gravity pulls, expansion stretches, matter flows, patterns form. Laniakea is one of these patterns. Its edge is where that pattern blends into the larger tapestry of the cosmos. In the next part, we will step even farther outward and examine what lies beyond Laniakea, the neighbouring superclusters, the immense cosmic voids, and the grand-scale architecture that places Laniakea within the larger map of the observable universe. Because understanding the edge of Laniakea is not the end of the journey, it is the gateway to an even greater cosmic landscape. Beyond the edge of Laniakea lies a universe that is even more complex, vast and interconnected than the supercluster itself suggests. When astronomers trace the gravitational boundaries of Laniakea outward, they do not find emptiness. Instead, they encounter neighbouring superclusters, immense voids, and sprawling filaments that weave together to form the grand architecture of the observable cosmos. Laniakea is not an isolated structure floating alone in space. It is one node within a colossal network. This network is the cosmic web, the largest known structure in the universe. It spans billions of light years and connects superclusters through filamentary bridges of matter and dark matter. These filaments act as conduits transporting galaxies' gas and energy between massive regions. One of the most significant neighbours of Laniakea is the Perseus-Pisces supercluster. This structure stretches across hundreds of millions of light years and contains thousands of galaxy clusters and groups. It lies along a massive filament that rivals Laniakea in scale. Although Perseus-Pisces is gravitationally distinct from Laniakea, the two are connected through the cosmic web, sharing matter flows along overlapping filamentary networks. Another dominant neighbour is the Shapley supercluster. Shapley is one of the most massive concentrations of matter in the nearby universe. Its gravitational influence is so strong that it affects galaxy motions across enormous distances. Some regions near the boundary of Laniakea experience competing gravitational pulls from both Shapley and Laniakea, creating complex motion patterns. These overlapping influences illustrate that superclusters do not exist in isolation. They interact indirectly through gravity and shared filamentary connections. Between these massive structures lie vast cosmic voids. Voids are regions where matter density is extremely low. They can span tens to hundreds of millions of light years and contain only sparse populations of galaxies. Far from being empty gaps, voids play a critical role in shaping the cosmic web. Matter flows away from voids and accumulates along their edges. This movement strengthens filaments and feeds superclusters. In this way, voids act as sculptors of cosmic structure, carving out the large-scale geometry of the universe. Around Laniakea, several major voids define its outer contours. These empty regions push matter inward toward dense clusters and filaments, reinforcing Laniakea's gravitational basin. Without voids, the cosmic web would not have its distinctive foam-like structure. The interplay between superclusters and voids creates a dynamic equilibrium. Dense regions grow denser, empty regions become emptier. This contrast drives the evolution of large-scale structure and maintains the overall pattern of the cosmic web. Beyond Laniakea, the scale of cosmic organization becomes difficult to visualize. Superclusters themselves are grouped into even larger structures, sometimes called supercluster complexes or walls. These massive formations can stretch across more than 1 billion light-years and contain multiple superclusters linked together by filaments. One example is the Sloan Great Wall, an enormous structure discovered through galaxy surveys that spans over 1 billion light-years. It contains thousands of galaxy clusters and represents one of the largest known features in the observable universe. Laniakea is smaller than some of these giant structures, but it remains one of the most significant gravitational basins in our local cosmic environment. Understanding Laniakea's position within this larger context reveals something important about cosmic scale. There is no single, largest structure in the universe. As observational technology improves, astronomers continue to discover ever larger patterns in the distribution of matter. What was once considered immense becomes part of a larger framework. This does not mean that structure extends infinitely without limit. It means that the universe organizes itself hierarchically. Small systems nest inside larger ones, galaxies inside clusters, clusters inside superclusters, superclusters inside cosmic walls and filaments. This nesting reflects the way gravity operates across scales. Gravity does not favor any particular size. It operates wherever mass exists. This scale-free nature of gravity allows structure to form across a vast range of distances. From planetary systems to cosmic filaments, the same fundamental force shapes everything. Another important feature beyond Laniakea is the presence of dark matter filaments. These filaments form the invisible skeleton of the cosmic web. They are composed primarily of dark matter, with ordinary matter falling into their gravitational wells. Galaxies form and evolve along these filaments, tracing their structure like beads on strings. When astronomers map the distribution of galaxies beyond Laniakea, they are effectively mapping these dark matter filaments indirectly. This reveals that the visible universe is only a surface layer of a much larger hidden framework. Most of the mass that shapes cosmic structure is invisible. This invisible architecture determines where superclusters form, how they connect, and how matter flows between them. Laniakea's location within this network reflects the underlying distribution of dark matter. It occupies a region where multiple filaments intersect, creating a gravitational hub that draws matter inward. Beyond these hubs, filaments stretch across cosmic voids, connecting distant superclusters in delicate strands of matter. These filaments are not rigid structures. They evolve over time. They grow thicker as matter accumulates. They thin as expansion stretches space. They can fragment or merge as gravitational influences change. This dynamic behavior means that the cosmic web itself is constantly changing. The map of superclusters today will not match the map billions of years in the future. Expansion driven by dark energy is gradually weakening the gravitational connections between distant structures. Over time, filaments will thin, connections between superclusters will weaken. Some regions will become causally isolated from others. This future evolution will reshape the cosmic landscape beyond Laniakea. What appears today as a connected web may eventually fragment into isolated islands of matter. This process will not happen suddenly. It will unfold over trillions of years, but it represents the long-term fate of large-scale cosmic structure. Understanding this future evolution helps place Laniakea in temporal context. It is not only a spatial structure, it is a moment in cosmic history. Laniakea exists during an era when gravity still competes effectively with expansion on large scales. In the far future, expansion will dominate. Superclusters will no longer function as coherent gravitational basins. They will become separated by ever-growing voids. This transformation highlights the transient nature of large-scale cosmic organization. Even the largest known structures are not permanent. They are shaped by cosmic conditions that evolve over time. Another important aspect of what lies beyond Laniakea is the distribution of cosmic background radiation. The cosmic microwave background permeates all of space and provides a reference frame for large-scale motion. By measuring how galaxies move relative to this background, astronomers can detect large-scale flows that extend beyond individual superclusters. These flows reveal that Laniakea is part of even larger motion patterns that span enormous regions of the universe. This suggests that superclusters themselves participate in collective motion relative to the overall expansion of space. Although expansion dominates on the largest scales, gravitational interaction still creates subtle bulk flows that affect large regions. These motions are small compared to cosmic expansion, but they provide valuable clues about the distribution of mass beyond visible structures. They hint at the presence of unseen matter concentrations and large-scale gravitational gradients. Studying these flows helps refine our understanding of cosmic structure beyond Laniakea. It allows astronomers to test cosmological models and probe the nature of dark matter and dark energy. This makes Laniakea not just an object of interest in its own right, but a tool for studying the broader universe. By analysing how matter flows into and out of Laniakea, scientists can learn about the forces shaping the entire cosmic web. Another fascinating aspect of the region beyond Laniakea is the extreme scale of cosmic voids. Some voids are so large that light takes hundreds of millions of years to cross them. These vast empty regions dominate the volume of the universe, even though they contain very little matter. From a volumetric perspective, the universe is mostly void. Matter is concentrated in thin filaments and dense nodes, occupying only a small fraction of space. This distribution has profound implications for cosmic evolution. Most of the universe is quiet, dark, and empty. Structure is rare and localized. Superclusters like Laniakea represent islands of complexity in a vast cosmic ocean of emptiness. This perspective emphasizes how special large-scale structures truly are. They are the result of billions of years of gravitational amplification, acting on tiny initial density fluctuations. Without these fluctuations, the universe would remain nearly uniform and featureless. Laniakea is therefore a testament to the power of small beginnings. Tiny irregularities in the early universe grew into immense structures that now shape the motion of galaxies across hundreds of millions of light years. Looking beyond Laniakea also highlights the limits of observation. As distance increases, galaxies become fainter and harder to detect. Beyond a certain point, even the largest telescopes struggle to observe individual structures. This observational limit means that our map of the cosmic web becomes less detailed at greater distances. There may be structures beyond our current observational reach that we have not yet discovered. Future telescopes and surveys will extend this reach, revealing new superclusters, filaments, and voids. Each new discovery will refine our understanding of how Laniakea fits into the broader cosmic picture. This ongoing expansion of knowledge mirrors the expansion of the universe itself. As technology advances, our view of cosmic structure grows more detailed and more complex. But it also becomes clear that there will always be limits. The observable universe is finite. Beyond its horizon lies unreachable space. Within that horizon, however, there remains an immense landscape of structure to explore. Laniakea occupies one region of this landscape. Beyond it lies an even greater network of matter and motion. Understanding this network transforms how we think about location in the universe. We are not located in isolation. We are embedded in a web of gravitational relationships that span enormous distances. Our galaxy's position within Laniakea is one layer of this embedding. Laniakea's position within the cosmic web is another. Each layer adds context. Each reveals deeper structure. In the next part, we will bring this exploration back toward our local environment and examine what Laniakea means for the Milky Way itself, how our galaxy's motion is shaped by the supercluster, where we are headed, and what our place within this vast structure reveals about our cosmic address. Because understanding Laniakea is not only about distant galaxies, it is also about understanding where we truly are in the universe. When the scale of Laniakea is fully understood, the Milky Way's place within it takes on a new meaning. Our galaxy is not floating freely in empty space. It is embedded inside a vast gravitational system that quietly shapes its motion, its environment, and its long-term future. To understand Laniakea is to understand our true cosmic address. The Milky Way belongs to a small collection of galaxies known as the Local Group. This group contains more than 50 galaxies, including Andromeda, the Triangulum galaxy, and many smaller dwarf galaxies. These galaxies are gravitationally bound to one another, forming a stable local system that will remain intact even as the larger universe continues to expand. Within the local group, the Milky Way and Andromeda dominate. They are locked in a slow gravitational dance that will eventually lead to a merger billions of years from now. This local interaction is strong enough to resist cosmic expansion. The local group behaves as a tightly bound island of matter, but beyond this immediate neighborhood lies a much larger context. The local group itself is part of a larger structure called the local sheet, a flattened arrangement of galaxies spanning tens of millions of light years. This sheet is embedded within filaments of the cosmic web that guide matter toward denser regions. These filaments connect the local sheet to the Virgo cluster, the nearest massive galaxy cluster and one of the central gravitational anchors of Laniakea. The Virgo cluster lies roughly 65 million light-years away and contains thousands of galaxies packed into a relatively small region of space. Although the Virgo cluster is distant by human standards, its gravitational influence extends far beyond its visible boundaries. The Milky Way is slowly drifting toward Virgo. This motion is not dramatic. It is not visible on human timescales, but precise measurements of galaxy velocities reveal that our local group is moving at several hundred kilometers per second relative to the cosmic microwave background. This motion reflects the combined gravitational pull of Virgo and other massive structures within Laniakea. This movement is part of a larger flow. Galaxies throughout Laniakea are migrating along gravitational gradients toward dense regions. The Milky Way is one participant in this collective motion. This realization changes how motion in space is understood. It is easy to imagine that galaxies simply move apart due to cosmic expansion. In reality, expansion and gravity operate simultaneously. Expansion pushes galaxies apart on large scales, while gravity pulls them together locally. The result is a complex pattern of motion. Galaxies move outward with expansion, while also drifting sideways and inward due to gravitational attraction. These combined motions create curved trajectories through space. The Milky Way's path through the universe is not a straight line. It is shaped by the gravitational landscape of Laniakea. This landscape includes not only Virgo, but also the Great Attractor region and other massive structures embedded within the supercluster. Together, these gravitational centers create a multi-directional pull that guides galaxy motion. Our galaxy is therefore not moving toward a single destination. It is responding to a network of gravitational influences. This network evolves over time as clusters grow, merge, and redistribute mass. Understanding this motion requires separating different layers of movement. First, there is Earth's motion around the Sun, then the Sun's motion within the Milky Way, then the Milky Way's motion within the local group, then the local group's motion within Laniakea, and finally Laniakea's motion relative to the broader cosmic web. Each layer adds velocity and direction, each layer reflects a different gravitational scale. Together they form a nested hierarchy of motion that extends from planetary orbits to supercluster flows. This nested structure shows that location in the universe is dynamic. There is no fixed cosmic coordinate system anchored to matter. Everything moves, everything flows. This constant motion does not create chaos. It creates structure. The flow of galaxies along filaments reinforces the cosmic web. Matter accumulates where gravity is strongest. Voids grow emptier as matter drains away. The Milky Way participates in this process simply by existing within it. Another important aspect of our location in Laniakea is environmental influence. Galaxies do not evolve in isolation. Their surroundings affect their structure, star formation, and long-term behavior. The Milky Way's location in a relatively low-density region of Laniakea has influenced its evolutionary history. Our galaxy is not located in the dense core of a massive cluster. It exists on the outskirts of large-scale filaments. This environment is relatively calm compared to the crowded interiors of clusters like Virgo. In dense clusters, galaxies experience frequent interactions and mergers. They are subjected to intense gravitational forces and high-energy environments filled with hot intergalactic gas. These conditions can strip gas from galaxies, suppress star formation, and alter galactic structure. The Milky Way has largely avoided these extreme environments. As a result, it has retained a significant amount of gas and continues to form new stars. Its spiral structure remains intact. Its evolution has been relatively gentle compared to galaxies trapped in cluster cores. This environmental advantage is a direct consequence of our position within Laniakea. We are close enough to massive structures to be influenced by their gravity, but far enough to avoid the most disruptive conditions. This balance has allowed the Milky Way to maintain long-term stability. It has also created favourable conditions for the development of complex structures, including planetary systems and life. While cosmology does not determine the emergence of life directly, the large-scale environment sets the stage on which galaxies evolve. Calm environments support stable star formation and long-lived stellar populations. Violent environments produce rapid evolution but also frequent disruption. The Milky Way's location has placed it in a relatively stable region of the cosmic web. Another important factor is the role of dark matter. The Milky Way is embedded within a dark matter halo that extends far beyond the visible disk. This halo interacts gravitationally with the surrounding dark matter filaments of Laniakea. These interactions influence the motion of the galaxy and its orientation within the cosmic web. Simulations show that galaxy spins and orientations are not random. They often align with nearby filaments and gravitational flows. This suggests that the Milky Way's orientation and angular momentum may be linked to the large-scale structure of Laniakea. In other words, the shape and rotation of our galaxy may carry the imprint of cosmic scale forces. This connection between local and large-scale structure highlights the deep integration of cosmic processes. Small-scale features emerge from large-scale patterns. Galaxies are shaped by the environment in which they form. Another implication of our position in Laniakea is the long-term future of our galaxy. As dark energy accelerates cosmic expansion, the large-scale structure of the universe will gradually fragment. Superclusters will lose gravitational coherence, filaments will thin, connections between distant regions will weaken. However, local gravitational systems like the local group will remain bound. The Milky Way and Andromeda will eventually merge to form a single, large galaxy. This merged galaxy will remain gravitationally bound and isolated as the rest of the universe recedes beyond observational reach. In this future, the memory of Laniakea may fade. Distant clusters will move beyond the cosmic horizon. The Virgo cluster will become invisible. The larger structure of the supercluster will no longer be observable. Future observers within the merged Milky Way Andromeda galaxy may not even be aware that Laniakea once existed. They will see a small, isolated group of galaxies surrounded by darkness. This illustrates how cosmic structure changes not only physically but observationally. What we can see today will not always be visible. Our current view of Laniakea exists within a narrow window of cosmic time. This makes our era unique. We live at a time when large-scale structure is still observable and traceable. We can map superclusters, we can measure galaxy flows, we can reconstruct cosmic architecture. This window will eventually close. Expansion will hide distant structures beyond the horizon. This gives added significance to current cosmological research. It is not simply about satisfying curiosity, it is about documenting a fleeting cosmic configuration. The structure of Laniakea, the position of the Milky Way within it, and the motion of galaxies across the cosmic web represent a moment in the universe's long history. Future generations may not have access to this information. This realization reframes the importance of understanding our cosmic address. It is not only about knowing where we are, it is about preserving knowledge of how the universe once looked. The Milky Way's location within Laniakea also provides a reference point for studying cosmology. By observing how nearby galaxies move relative to us, scientists can infer the distribution of mass and test models of cosmic expansion. Our position inside Laniakea allows us to study both local and large-scale structure simultaneously. This dual perspective is valuable. It connects detailed observations of nearby galaxies with broader patterns of cosmic motion. It allows scientists to calibrate models of structure formation. It provides insight into how gravity and expansion interact across scales. In this sense, the Milky Way's location is scientifically advantageous. We are embedded within a rich region of cosmic structure that offers opportunities for observation and analysis. This does not make our position special in a cosmic sense. It simply reflects the fact that we exist in a region where large-scale structure is prominent and observable. As the exploration of Laniakea continues, new data will refine our understanding of the Milky Way's motion and environment. Future surveys will map additional galaxies, reveal hidden filaments, and uncover new clusters. These discoveries will add detail to the picture of our cosmic neighborhood. They will show that our location is part of an even more complex web of gravitational relationships. The Milky Way is not a solitary island. It is one node in a vast network of matter and motion. Understanding this network changes how we view the night sky. Each galaxy becomes not just a distant object, but part of a larger flow. Each cluster becomes not just a group of galaxies, but a gravitational anchor shaping cosmic currents. Each filament becomes not just a faint structure, but a channel of matter connecting distant regions. Laniakea is the framework that connects all of these elements in our local universe. And within this framework, the Milky Way continues its slow journey through space, guided by invisible forces that have been shaping the universe since its earliest moments. In the next part, we will explore how scientists visualize Laniakea and the cosmic web, how data is transformed into three-dimensional maps, and how these visual tools allow us to see structures that are otherwise invisible to the human eye. Because to truly trace the edge of Laniakea, we must first learn how to see the universe in motion. Tracing Laniakea does more than reveal a massive supercluster. It changes the way the universe itself is understood. The discovery of this structure forces a shift in perspective, from viewing space as a scattered collection of galaxies to seeing it as an organized system shaped by gravity, motion, and deep cosmic connectivity. For centuries, humanity's view of the cosmos has expanded in stages. First came the realization that Earth is not the center of the universe. Then the understanding that the Sun is only one star among billions in the Milky Way. Later, astronomers discovered that the Milky Way is just one galaxy among trillions. Now Laniakea adds another layer. It shows that galaxies themselves are not isolated islands. They belong to vast gravitational regions that stretch across hundreds of millions of light years. This layered structure reshapes how cosmic scale is interpreted. It reveals that the universe is not simply large, it is hierarchically organized. Each level of structure nests within a larger one, creating a complex architecture that extends across enormous distances. This realization has deep implications for cosmology. It confirms predictions made by theoretical models of structure formation. These models suggested that matter should organize itself into filaments and superclusters due to the influence of gravity acting on early density fluctuations. The discovery of Laniakea provides observational evidence that these models accurately describe reality. It shows that the cosmic web is not an abstract concept. It is a physical structure that can be mapped, measured, and analyzed. This strengthens confidence in the underlying physical laws that govern cosmic evolution. It also refines understanding of dark matter. Because Laniakea's structure is dominated by invisible mass, its discovery highlights the central role of dark matter in shaping the universe. Without dark matter, superclusters would not form in the way they do. The gravitational scaffolding that supports the cosmic web would not exist. Laniakea therefore serves as indirect evidence for the presence and influence of dark matter. It shows how unseen matter controls the motion of visible galaxies. This has implications beyond large-scale structure. It affects galaxy formation, cluster evolution, and the distribution of matter throughout the universe. Tracing Laniakea also improves understanding of cosmic flows. By studying how galaxies move within the supercluster, scientists gain insight into the distribution of mass and the balance between gravity and expansion. These flow patterns reveal how matter is redistributed over time. They show where mass accumulates. They indicate where voids grow. They expose the dynamic nature of the cosmic web. This dynamic perspective challenges the idea of a static universe. Even on the largest scales, the universe is constantly evolving. Structures grow, boundaries shift, flows change. Laniakea is not a frozen object. It is a moving pattern. This movement provides clues about the universe's past and future. By tracing current flows, scientists can infer the history of mass distribution. They can reconstruct how matter moved over billions of years. They can predict how it will continue to move as expansion accelerates. This ability to connect past, present, and future is one of the most powerful aspects of modern cosmology. It turns observation into a time machine. Another important implication of Laniakea is its impact on how cosmic boundaries are defined. Traditional maps of the universe were based on visible clustering. Galaxies were grouped by proximity. Superclusters were defined by density alone. Laniakea introduced a new approach. It defined cosmic regions by motion rather than position. This shift has broad consequences. It suggests that gravitational influence is a more meaningful way to define structure than simple spatial grouping. Two galaxies may appear close together, but belong to different gravitational basins. Conversely, galaxies far apart in distance may share the same flow pattern. This redefinition of structure emphasizes connectivity over proximity. It reflects the reality that gravity acts across space and shapes motion. This perspective could reshape future classifications of cosmic structures. As more data becomes available, astronomers may redefine other superclusters using similar flow-based methods. This would create a new map of the universe based on gravitational relationships rather than purely geometric boundaries. Such a map would provide deeper insight into the true architecture of cosmic structure. Laniakea also highlights the limits of human intuition. The scale involved is so vast that it challenges ordinary understanding. Hundreds of millions of light years are difficult to visualize. Gravitational flows unfolding over billions of years are impossible to experience directly. Yet through data and visualization, scientists can reconstruct these processes. This demonstrates the power of scientific abstraction. It allows humanity to comprehend phenomena far beyond direct perception. It shows that understanding the universe requires new ways of thinking. It requires letting go of everyday intuition and embracing mathematical and conceptual models. This shift in perspective has philosophical implications. It raises questions about humanity's place in the cosmos. When the Milky Way is seen as a small component of a vast supercluster, and that supercluster is seen as one node in a larger cosmic web, the scale of the universe becomes humbling. It emphasizes how small any individual galaxy is relative to the whole. At the same time, it highlights how connected everything is. The motion of our galaxy is influenced by structures hundreds of millions of light years away. Our cosmic environment is shaped by forces far beyond our local neighborhood. This interconnectedness challenges the idea of isolation. It suggests that even at the largest scales, the universe is a network of relationships. Everything influences everything else, directly or indirectly. This realization has cultural and philosophical resonance. It echoes ideas of interconnection found in many human traditions now grounded in physical reality. Another implication of Laniakea is its relevance to observational strategy. Understanding large-scale structure helps astronomers plan surveys and observations. Knowing where filaments and clusters are located allows researchers to target regions of interest. It helps identify environments where galaxy evolution may differ. It guides the search for rare cosmic phenomena. For example, regions where filaments intersect are likely to host massive clusters and energetic events. Targeting these regions increases the likelihood of observing extreme astrophysical processes. Similarly, studying galaxies in voids provides insight into how environment influences evolution. Laniakea's map therefore becomes a practical tool for research. It informs observational priorities, it shapes the design of future surveys, it provides context for interpreting data. Another important consequence is the impact on cosmological measurements. Large-scale flows can influence measurements of cosmic expansion. If galaxy motions are not properly accounted for, they can introduce errors into estimates of the Hubble constant and other cosmological parameters. Understanding the structure of Laniakea helps correct for these effects. It allows scientists to separate local motion from global expansion more accurately. This improves the precision of cosmological measurements. It helps resolve discrepancies between different observational methods. It contributes to refining the standard model of cosmology. In this way, Laniakea plays a role in fundamental physics. It is not just a map feature. It influences how the universe's expansion is measured and understood. Another implication involves the study of cosmic anisotropy. If large-scale structures like Laniakea create bulk flows of matter, they could produce subtle directional effects in cosmic observations. Studying these effects helps test whether the universe is truly homogeneous and isotropic on large scales. Current evidence suggests that the universe is remarkably uniform when viewed at sufficiently large scales. However, structures like Laniakea represent deviations from perfect uniformity. Understanding these deviations helps refine models of cosmic evolution. It ensures that theoretical assumptions match observed reality. Laniakea also serves as a reminder of the limits of current knowledge. Although the supercluster has been mapped, uncertainties remain. Some regions are poorly observed, some flow patterns are inferred indirectly. Some mass concentrations remain hidden behind dust and gas. Future observations may reveal new features. They may modify current boundaries. They may change the perceived shape of the supercluster. This uncertainty is part of the scientific process. It reflects the complexity of the universe and the challenges of observing it. It also highlights the importance of continued exploration. Each new dataset brings more clarity and more questions. Another important aspect is the educational impact. The concept of Laniakea provides a powerful way to teach about large-scale structure. It offers a concrete example of how galaxies are organized. It illustrates abstract concepts such as gravitational flow, cosmic expansion, and dark matter. It helps people visualize the universe as a structured system rather than a random collection of objects. This educational value extends beyond astronomy. It demonstrates how scientific models are built. It shows how data is transformed into understanding. It reveals the process of discovery. This makes Laniakea a valuable case study in scientific methodology. It shows how observation, theory, and computation work together to reveal hidden aspects of reality. Finally, tracing Laniakea raises questions about the future of cosmic mapping. As technology improves, astronomers will be able to map larger volumes of space with greater precision. They will detect fainter galaxies. They will measure velocities more accurately. They will reconstruct flow patterns across greater distances. This will allow scientists to trace superclusters beyond Laniakea and refine the map of the cosmic web. It may reveal even larger structures. It may change how superclusters are defined. It may uncover new patterns in the distribution of matter. This future work will continue the process of expanding humanity's cosmic perspective. Each new discovery pushes the boundary of what is known. Each new map adds detail to the picture of the universe. Laniakea represents a milestone in this journey. It is a step toward understanding the true scale and structure of the cosmos, but it is not the final step. The universe remains vast, complex, and full of hidden structure. Tracing Laniakea has shown that even the largest known structures are part of something even larger. It has revealed a universe shaped by motion, gravity, and connection, and in doing so, it has changed how humanity sees its place in the cosmic story. In the final part, we will bring together everything explored so far: the formation of Laniakea, its structure, its boundaries, its connection to the cosmic web, and its meaning to understand what tracing the edge of this immense supercluster ultimately tells us about the universe and our place within it. Tracing the edge of Laniakea ultimately leads to a deeper question that goes beyond maps, data, and cosmic flows. What does it mean to understand our place inside such an immense structure? When scientists describe superclusters, filaments, and voids, they are not only charting matter in space, they are redefining how humanity understands scale, connection, and the nature of cosmic belonging. For most of human history, the universe was perceived as small and centered around Earth. The stars were thought to be fixed points embedded in a celestial sphere. Over time, this view collapsed. The Earth lost its central position. The Sun became one star among many. The Milky Way became one galaxy among billions. Now, Laniakea adds another layer to this expanding realization. It reveals that even galaxies are not isolated. They are embedded within gravitational systems so large that the human mind struggles to fully comprehend them. This realization does not diminish the significance of the Milky Way. It reframes it. Our galaxy is not central, but it is connected. It is part of a structure that spans hundreds of millions of light years and contains more than 100,000 galaxies. This connection challenges the idea that cosmic scale is defined by isolation. Instead, scale is defined by networks. The universe is not a collection of separate objects. It is a web of relationships. Every galaxy participates in gravitational flows that link it to distant structures. Every cluster is influenced by mass concentrations far beyond its immediate neighborhood. Laniakea is one example of this cosmic interconnectedness. Understanding this interconnectedness has practical implications for cosmology. It changes how researchers interpret observations. When astronomers observe a galaxy, they no longer see it as a standalone object. They consider its environment. They ask which filament it belongs to, which cluster influences it, which supercluster basin shapes its motion. This environmental context helps explain differences in galaxy behavior. It explains why some galaxies evolve rapidly while others remain stable for billions of years. It explains why star formation rates vary. It explains why certain regions host intense activity while others remain quiet. The environment matters. Laniakea provides a framework for understanding that environment on the largest scales. It offers a reference system for interpreting cosmic data. It contextualizes local observations within a much larger structure. This contextual understanding also influences how cosmological theories are tested. Models of the universe must account not only for average properties, but also for large-scale structure. They must reproduce the formation of superclusters, filaments, and voids. They must explain why structures like Laniakea exist. They must predict the observed flow patterns of galaxies. When models succeed in reproducing these features, confidence in their accuracy increases. When they fail, new physics may be required. Laniakea therefore serves as a benchmark for testing cosmological models. It is a large-scale laboratory for studying gravity, dark matter, and cosmic expansion. Another implication involves the nature of cosmic boundaries. Tracing Laniakea shows that boundaries in the universe are not sharp lines. They are gradual transitions defined by motion and influence. This challenges the way boundaries are usually imagined. Instead of walls, the universe is divided by flow patterns. Instead of borders, it has gravitational watersheds. This fluid definition of structure reflects the dynamic nature of the cosmos. It shows that the universe is not static. It is constantly reorganizing itself. Matter flows, structures evolve, connections change. This dynamic view aligns with the idea that the universe is a process rather than a fixed object. It is not a finished product. It is an ongoing evolution. Understanding this process-oriented nature of the universe has philosophical implications. It suggests that reality is defined by change and interaction. It emphasizes motion over position. It highlights relationships over isolation. This perspective resonates with modern physics, which increasingly describes reality in terms of fields, interactions, and dynamic systems. Laniakea fits naturally into this framework. It is not a solid object. It is a pattern of motion. Another important consequence of tracing Laniakea is its impact on how humanity views its long-term future. As discussed earlier, the accelerated expansion of the universe will eventually isolate gravitationally bound systems. Over trillions of years, distant galaxies will fade beyond the cosmic horizon. Superclusters will fragment. Connections between regions will weaken. In this future, the memory of structures like Laniakea may disappear from observational reality. Future civilizations may see only their local group of galaxies surrounded by darkness. This means that our current view of large-scale structure is temporary. We exist during a unique era when the cosmic web is still visible. This makes current cosmological research historically significant. It is documenting a universe that future observers may not be able to see. Understanding Laniakea is therefore not only about present knowledge, it is about preserving a record of cosmic structure during a fleeting window of observability. This adds urgency and importance to large-scale mapping projects. They are capturing information that may become inaccessible in the distant future. Another implication involves the psychological effect of cosmic scale. When people learn about structures like Laniakea, they often experience a sense of awe. This reaction is not accidental. The scale involved is far beyond everyday experience. It challenges assumptions about size, distance, and significance. This sense of awe can be scientifically productive. It encourages curiosity, it motivates exploration. It inspires deeper questions about the nature of reality. Laniakea serves as a reminder that the universe is far larger and more complex than it appears from Earth. It invites people to look beyond the familiar and engage with the unknown. This cultural impact of cosmology should not be underestimated. Scientific discoveries shape how societies view themselves. They influence philosophy, art, and worldview. The discovery of Laniakea contributes to this ongoing cultural evolution. It reinforces the idea that humanity is part of a much larger cosmic system. It challenges anthropocentric perspectives. It promotes a more universal view of existence. Another important aspect of tracing Laniakea is the demonstration of scientific collaboration. Mapping a structure of this scale requires cooperation between researchers across the world. It involves data from multiple telescopes, surveys, and institutions. It requires expertise in astronomy, physics, computer science, and statistics. This collaborative effort reflects the global nature of modern science. It shows that understanding the universe is a collective endeavor. No single researcher or institution could map Laniakea alone. It requires shared data, shared tools, and shared knowledge. This collaborative model is becoming increasingly important as scientific questions grow more complex. Laniakea is an example of how large-scale scientific challenges can be addressed through cooperation. It demonstrates the power of collective intelligence. Another consequence of tracing Laniakea is the refinement of scientific methodology. The techniques used to reconstruct flow patterns and gravitational fields represent advanced applications of data analysis and modeling. These methods can be applied to other areas of astrophysics and beyond. They contribute to the development of new computational tools and analytical techniques. This cross-disciplinary impact extends the significance of Laniakea beyond cosmology. It influences data science, simulation technology, and visualization methods. The tools developed for cosmic mapping can be adapted for other complex systems. This illustrates how fundamental research often produces broader technological and methodological benefits. Another implication is the role of uncertainty. Mapping Laniakea involves dealing with incomplete data, measurement errors, and model assumptions. Scientists must carefully quantify uncertainty and avoid overconfidence in their results. This emphasis on uncertainty is a core principle of scientific practice. It ensures that conclusions remain open to revision. It encourages continuous improvement of models and methods. Tracing Laniakea, therefore, also serves as an example of how science manages uncertainty while still producing meaningful knowledge. It shows that understanding does not require absolute certainty. It requires careful analysis, transparency, and willingness to update conclusions as new data becomes available. Finally, tracing Laniakea highlights the power of human curiosity. The desire to understand where we are in the universe is deeply rooted in human nature. From ancient star charts to modern cosmic maps, humanity has always sought to locate itself within the larger cosmos. Laniakea represents the latest chapter in this long story. It is a modern answer to an ancient question: where are we? The answer today is more complex than ever. We are on a planet orbiting a star, inside a galaxy, inside a local group, inside a supercluster, inside a cosmic web. Each layer adds context. Each layer expands perspective. This layered understanding does not make the universe feel smaller. It makes it feel richer. It reveals depth, structure, and connection. Tracing the edge of Laniakea shows that even the largest structures we can map are part of something even greater. It reveals a universe shaped by invisible forces, dynamic flows, and intricate patterns. It shows that our place in the cosmos is not defined by centrality, but by connection. And in that connection, humanity finds both humility and wonder. Because to understand Laniakea is not just to trace a supercluster, it is to glimpse the true scale of the universe and to recognize that we are part of a vast cosmic story that continues to unfold. Tracing Laniakea to its deepest implications ultimately brings the journey full circle, back to the question of meaning. Not meaning in a mystical sense, but meaning in the scientific sense. What this immense structure tells us about the universe, about physical law, and about humanity's evolving understanding of reality. Laniakea exists because gravity obeys simple rules. Mass attracts mass. Small differences grow larger over time. Expansion stretches space. Dark matter provides invisible structure. From these basic principles, complexity emerges. Filaments form, clusters grow, superclusters take shape. What makes Laniakea remarkable is not that it exists, but that such enormous organization arises naturally from simple physical laws operating over vast spans of time. This reinforces one of the central ideas of modern cosmology. The universe is not chaotic, it is ordered, but not rigid. Its order is dynamic, adaptive, and scale-dependent. Patterns appear at every level, from atomic structure to cosmic webs. Laniakea is one expression of this universal tendency towards structure. It shows that complexity does not require design. It emerges from interaction. Another lesson from Laniakea is the importance of scale. At small scales, gravity binds stars into galaxies. At medium scales, galaxies form clusters. At large scales, clusters merge into superclusters. At the largest scales, expansion dominates, and structure fades into uniformity. Each scale obeys the same physical laws, but the outcomes differ. This layered behavior challenges the idea that one perspective can fully describe the universe. Understanding reality requires moving between scales. It requires connecting local processes with global patterns. Laniakea provides a bridge between these scales. It links the motion of individual galaxies to the architecture of the cosmic web. This bridging role makes superclusters especially valuable for understanding how the universe transitions between order and uniformity. They exist at the boundary where gravity and expansion compete. They reveal the balance between attraction and separation. They show where structure thrives and where it begins to dissolve. This boundary region is where the universe is most dynamic and informative. Another important implication of Laniakea is its role in testing the limits of cosmological models. The standard model of cosmology predicts the formation of large-scale structure through the growth of initial density fluctuations. Laniakea provides a real-world example that can be compared directly with simulation results. When simulations reproduce similar superclusters, filaments, and flow patterns, it strengthens confidence in the model. When discrepancies appear, they point toward gaps in understanding. These gaps can reveal new physics. They may suggest modifications to dark matter behavior. They may indicate unknown properties of dark energy. They may hint at subtle effects in gravity itself. In this way, Laniakea is not just a structure to be described, it is a test environment for fundamental physics. Another lesson from tracing Laniakea is the importance of motion. Cosmic structure is not defined solely by where things are. It is defined by how they move. This emphasis on motion aligns with the deeper principles of physics. From relativity to quantum mechanics, motion, interaction, and change are central. Laniakea shows that even on the largest scales, motion is the key to understanding structure. It is not enough to know the position of a galaxy. One must know its velocity. One must know its direction. One must know its gravitational context. This dynamic view of the universe is more accurate than static maps. It reflects the reality that the cosmos is not frozen in time. It is constantly evolving. Another implication involves the role of observation itself. Mapping Laniakea required combining data from many instruments, wavelengths, and surveys. It required overcoming observational limits such as dust obscuration, distance uncertainty, and incomplete sky coverage. This process demonstrates how scientific knowledge is constructed. It is not the result of a single observation. It is the result of synthesis. Data is gathered. Models are built. Predictions are tested. Visualizations are refined. Each step adds clarity. Each step produces uncertainty. Laniakea is therefore also a story about scientific methodology. It shows how complex phenomena can be understood through careful analysis and collaboration. Another important aspect is the realization that our current cosmic map is temporary. As technology advances, the picture of Laniakea will become more detailed. New galaxies will be added. Hidden filaments will be revealed. Boundaries will be refined. At the same time, the universe itself is changing. Expansion will alter large-scale structure. Connections will weaken. Some regions will disappear beyond the cosmic horizon. This dual evolution of knowledge and of the universe itself highlights the fleeting nature of cosmic understanding. We are mapping a universe that is not static. We are capturing a moment in its history. This gives present-day cosmology a sense of urgency and significance. Another implication of tracing Laniakea is the shift in how humanity perceives its cosmic position. For much of history, humans searched for centrality. Was Earth at the center? Was the Sun? Was the Milky Way? Each time, the answer moved outward. Laniakea continues this trend. It shows that there is no central location in the universe. There are only networks of structure. There are only regions of influence. There is no privileged position. This realization can be unsettling. It removes the idea of cosmic importance tied to location, but it also offers a different kind of significance. Significance through participation. We are part of the cosmic web. Our galaxy participates in gravitational flows. Our matter originated in ancient stars. Our atoms were forged in cosmic processes that predate the Milky Way itself. In this sense, humanity is not separate from the universe. It is a product of it. Tracing Laniakea reinforces this continuity. It shows that the same physical laws that shape superclusters also shape the elements in our bodies. The same gravity that guides galaxies also binds planets. The same expansion that stretches space also defines the limits of observation. Everything is connected through shared physical principles. Another lesson from Laniakea is the role of patience in cosmic understanding. The structures being studied formed over billions of years. Their evolution unfolds on timescales far beyond human experience. Yet through observation and modelling, scientists can reconstruct these slow processes. They can compress billions of years into understandable narratives. This ability to transcend human timescales is one of science's greatest achievements. It allows humanity to see beyond the limits of direct experience. It allows us to understand processes that would otherwise remain invisible. Tracing Laniakea is part of this broader effort to understand deep time. It connects the present universe to its ancient origins and distant future. It shows that the cosmos has a history, it has a direction, it has an evolving structure. Another important implication is the emotional impact of cosmic scale. While science focuses on data and models, the human response to discoveries like Laniakea often includes awe, humility, and curiosity. These emotions are not separate from scientific inquiry. They motivate exploration. They inspire learning. They encourage people to ask deeper questions. Laniakea provides a powerful example of how scientific discovery can shape worldview. It expands perspective. It challenges assumptions. It invites reflection. Finally, tracing the edge of Laniakea brings clarity to one central idea. The universe is not defined by emptiness. It is defined by structure. Even in regions where matter is sparse, there are patterns. Even in vast voids, there is organization. Even at the largest scales, the universe is not random. It is shaped by simple laws acting over immense distances and times. Laniakea is one expression of this universal order. It is not the largest structure, it is not the final discovery, but it is a milestone. It represents humanity's growing ability to map reality on its grandest scales. It shows how far understanding has progressed, and it hints at how much more remains to be discovered. Because beyond Laniakea lie other superclusters, beyond the cosmic web lies the observable horizon, beyond that horizon lies unknown space. Each boundary invites exploration. Each discovery raises new questions. Tracing Laniakea is not the end of the story. It is part of an ongoing journey to understand the universe as a whole, a journey driven by curiosity, a journey guided by science, a journey that continues to expand humanity's view of reality. And as long as the universe continues to evolve, there will always be new edges to trace, new structures to map, and new perspectives to uncover. Because the true significance of Laniakea is not only what it reveals about the cosmos, It is what it reveals about humanity's capacity to understand it. When the journey of tracing Laniakea is extended even further, beyond scientific analysis and philosophical reflection, it becomes clear that this immense structure represents something deeper than a map of galaxies. It represents a turning point in how humanity interacts with the universe, not as distant observers, but as participants within a dynamic cosmic system. Laniakea shows that the universe is not simply something we look at, it is something we are inside. Every atom in the Milky Way participates in the same physical processes that shape superclusters. The matter that forms stars, planets, and living organisms originated in earlier generations of cosmic evolution. The heavy elements in our bodies were forged in ancient stars that lived and died long before the Milky Way settled into its current position within the cosmic web. This continuity connects the smallest scales of life to the largest scales of cosmic structure. The discovery of Laniakea reinforces this connection. It shows that local existence is embedded within global structure. Our galaxy's motion is influenced by distant clusters. Our cosmic environment is shaped by gravitational patterns extending across hundreds of millions of light years. There is no sharp separation between here and out there. Everything exists within a shared gravitational framework. This realization reshapes the concept of isolation. On Earth, isolation is defined by distance and separation. In the universe, isolation is relative. Even galaxies separated by vast distances are linked through gravitational influence and shared cosmic history. They formed from the same primordial matter. They evolved under the same physical laws. They are connected through the cosmic web. Laniakea makes this connectivity visible. It turns abstract ideas about cosmic unity into measurable structure. Another important dimension of tracing Laniakea is the way it challenges human perception of permanence. Cities, mountains, and even continents appear permanent on human timescales. In cosmic terms, they are momentary. Galaxies evolve, clusters merge. Superclusters reshape themselves. Even the cosmic web itself will eventually thin and fragment under the influence of dark energy. Laniakea exists within this long arc of change. It is stable on billion-year timescales, but not eternal. This impermanence is not a flaw, it is a natural consequence of an evolving universe. Understanding this helps reframe expectations about cosmic structure. The universe is not a static museum of objects. It is a dynamic system in constant motion. Every structure observed today is part of an ongoing transformation. This perspective has important implications for how scientific knowledge is interpreted. Maps of Laniakea represent a snapshot. They capture a moment in cosmic history. They do not represent a final configuration. Future maps will look different as new data is gathered and the universe continues to evolve. This means that scientific understanding is inherently provisional. It improves over time. It adapts to new evidence. It evolves alongside the universe it describes. Laniakea embodies this process. Its discovery was made possible by advances in observational technology, computational modeling, and theoretical understanding. It reflects the current state of cosmology. Future discoveries may expand or revise this picture. This does not weaken the significance of Laniakea, it strengthens it. It shows that knowledge is not static, it is a living process. Another implication of tracing Laniakea is the shift in how humanity understands exploration. For much of history, exploration meant travelling across land or sea. In the modern era, it expanded to space. Now, exploration increasingly takes the form of data analysis and conceptual mapping. Scientists explore regions of space they will never physically visit. They reconstruct structures far beyond the reach of spacecraft. They map invisible matter and gravitational flows. Laniakea is a product of this new form of exploration. It was not discovered by sending probes. It was discovered by combining observation with computation. This represents a new phase of cosmic exploration, one that relies on information rather than physical travel. This shift does not reduce the sense of discovery, it amplifies it. It allows humanity to explore scales that would otherwise remain inaccessible. It expands the frontier of knowledge beyond physical limitations. Another dimension of tracing Laniakea is the role of technology. Large-scale surveys, advanced telescopes, and powerful computers were essential to this discovery. Without precise distance measurements and velocity data, the flow patterns defining Laniakea would remain hidden. Without computational models, the gravitational structure could not be reconstructed. This highlights the interdependence of science and technology. Progress in one enables progress in the other. Future discoveries of even larger structures will depend on further technological advancement, more sensitive instruments, faster data processing, more sophisticated modeling techniques. Laniakea represents a milestone along this technological trajectory. It demonstrates what becomes possible when observation and computation are combined at scale. Another important aspect is the educational impact of cosmic mapping. Visualizations of Laniakea and the cosmic web provide powerful tools for teaching. They allow students and the public to see abstract concepts in concrete form. They transform mathematical models into visual structures. They make cosmic scale more intuitive. This educational value extends beyond astronomy. It teaches systems thinking. It demonstrates how complex patterns emerge from simple rules. It illustrates the importance of data interpretation and modeling. Laniakea therefore contributes not only to scientific knowledge, but to scientific literacy. It helps people understand how science works, how data becomes insight, how models are tested and refined. This broader impact is essential for maintaining public engagement with science. Another implication of tracing Laniakea is the reminder that the universe is still largely unknown. Even with modern technology, only a fraction of cosmic structure has been mapped in detail. Large regions remain unexplored. Hidden structures remain undetected. Unknown phenomena may exist beyond current observational limits. Laniakea itself was unknown until recently. This suggests that the universe still holds many surprises. Future discoveries may reveal new types of large-scale organization. They may challenge existing models. They may require new physical explanations. This uncertainty is not a limitation. It is an invitation. It encourages continued exploration. It motivates scientific curiosity. It keeps the process of discovery alive. Another dimension of tracing Laniakea is its influence on how humanity imagines the future. As knowledge of cosmic structure expands, it shapes long-term thinking. It influences ideas about interstellar travel, cosmic communication, and the limits of exploration. Understanding that the Milky Way is embedded within a supercluster highlights the immense distances involved in any attempt to travel beyond our local environment. It emphasizes the challenges of reaching even nearby clusters. It reveals the scale of the universe as both inspiring and limiting. At the same time, it provides context for humanity's ambitions. It shows where we are. It shows how far there is to go. It frames exploration within a realistic understanding of cosmic scale. Another important aspect is the role of perspective. Tracing Laniakea forces a shift from local to global thinking. It encourages viewing Earth not as a central reference point, but as part of a much larger system. This shift has implications beyond science. It influences worldview. It promotes a sense of shared existence. It emphasizes that humanity occupies a small part of a vast universe. This perspective can foster humility. It can encourage cooperation. It can reduce the tendency to view local conflicts as absolute. When seen in cosmic context, many human divisions appear small. This does not diminish human experience, it contextualizes it. It places it within a broader framework of existence. Another implication of tracing Laniakea is the recognition that discovery is cumulative. The identification of this supercluster was built on decades of prior research, early galaxy catalogues, redshift surveys, Theoretical models, computational advances, each contributed to the final picture. This cumulative nature of science highlights the importance of long-term investment in research. Breakthroughs rarely occur in isolation. They emerge from sustained effort. Laniakea is a product of this collective progress. It represents the combined work of many scientists across generations. This collaborative continuity is one of science's greatest strengths. It allows knowledge to build over time. It enables increasingly complex discoveries. Finally, tracing Laniakea invites reflection on the nature of cosmic storytelling. Humans have always told stories about the universe, myths, legends, cosmologies. Modern science continues this tradition, but with evidence-based narratives. Laniakea adds a new chapter. It tells a story of gravity shaping structure, of matter flowing across vast distances, of galaxies forming part of a greater whole. This story is not static. It evolves as new data is gathered. The economic field M is known as bones. It grows richer as understanding deepens. It connects humanity to a larger cosmic narrative that spans billions of years. Tracing Laniakea is therefore not only a scientific achievement, it is a cultural one. It expands humanity's collective understanding of where we are and how we fit into the universe. It reveals that the cosmos is not empty. It is structured, it is dynamic, it is interconnected, and within this vast structure, the Milky Way continues its quiet journey, guided by forces that have shaped the universe since its earliest moments. Laniakea stands as a reminder that even on the grandest scales, the universe is governed by simple laws that give rise to extraordinary complexity. It shows that exploration does not end at physical boundaries. It continues wherever curiosity reaches, and as long as humanity continues to ask questions about the universe, there will always be new structures to trace, new connections to uncover, and new perspectives to discover. Because the story of Laniakea is not just about one supercluster, it is about the ongoing effort to understand the cosmos itself. Tracing Laniakea to its furthest conceptual horizon brings the journey into a quiet but profound realization. The universe is not only something that can be measured, mapped, and modeled, it is something that invites continuous reinterpretation. Every new structure discovered, every boundary traced, every flow reconstructed reshapes the story humanity tells about reality itself. Laniakea represents one of those moments when understanding crosses a threshold. Before its discovery, superclusters were seen as loose groupings of galaxies defined mostly by proximity. After Laniakea, superclusters became dynamic gravitational domains defined by motion and influence. This shift is subtle but powerful. It changes how scientists think about cosmic organization. It replaces static categories with fluid systems. It reframes structure as process rather than object. This reframing aligns with a broader trend in modern science. Across disciplines, reality is increasingly understood as networks, interactions, and evolving systems. Biology studies ecosystems rather than isolated organisms. Physics studies fields and interactions rather than standalone particles. Cosmology now studies gravitational flows and cosmic webs rather than isolated galaxies. Laniakea fits naturally into this systems-based view of the universe. It shows that even the largest structures are not self-contained. They exist because of relationships. They persist because of balance. They evolve because of motion. This systems perspective has important consequences for how future research will unfold. Rather than focusing solely on individual galaxies or clusters, scientists will increasingly study connectivity, how matter moves between regions, how filaments transport gas, how gravitational influence propagates across space. This approach will reveal deeper layers of cosmic organization. It will uncover patterns that are invisible when objects are studied in isolation. Laniakea is an early example of what this network-based cosmology looks like in practice. Another lasting implication of tracing Laniakea is the refinement of cosmic scale awareness. Numbers like millions and billions of light-years lose meaning when repeated too often. They become abstract. But when those numbers are tied to structure, to visible filaments, to flowing galaxies, to gravitational basins, they become tangible. Laniakea gives scale a form. It transforms distance into shape. It turns expansion into motion. It allows the human mind to grasp otherwise incomprehensible magnitudes. This ability to translate scale into structure is one of science's most powerful tools. It bridges the gap between mathematics and intuition. It allows people to understand the universe not just intellectually, but visually and conceptually. Another important realization that emerges from tracing Laniakea is the universality of physical law. The same gravitational principles that guide falling objects on Earth govern the motion of galaxies across hundreds of millions of light years. The same expansion of space that stretches into galactic distances also influences the evolution of superclusters. There is no separate set of cosmic rules. There is one unified framework operating across all scales. This universality reinforces the coherence of the physical universe. It shows that reality is not fragmented. It is consistent. It obeys the same principles everywhere. Laniakea exists because those principles operate reliably over vast distances and times. This reliability is what makes scientific prediction possible. It allows models to be tested. It allows future evolution to be estimated. It allows the behavior of distant structures to be inferred from known laws. Tracing Laniakea therefore strengthens confidence in the fundamental unity of physics. Another consequence of this discovery is the way it reshapes scientific imagination. Once superclusters are understood as dynamic flow regions, new questions emerge. Are there even larger gravitational basins beyond current maps? Do superclusters themselves participate in higher-level flow patterns? How far does this hierarchy extend? Does the cosmic web contain structures that exceed current observational limits? These questions push cosmology toward deeper exploration. They motivate the development of larger surveys and more sensitive instruments. They inspire theoretical work aimed at understanding the limits of cosmic structure. Laniakea does not close inquiry, it opens new pathways. Another dimension of tracing Laniakea is the role of perspective in shaping knowledge. The discovery of this supercluster depended on adopting a new viewpoint, one focused on velocity and motion rather than static position. This shift illustrates how perspective determines what can be seen. By changing the question from "where are galaxies" to "where are galaxies going?", scientists uncovered an entirely new layer of structure. This lesson extends beyond cosmology. It shows that new discoveries often arise from asking different questions, from reframing problems, from viewing data through new conceptual lenses. Laniakea is therefore also a reminder of the creative aspect of science. Discovery is not only about collecting data, it is about interpretation, it is about insight. It is about finding new ways to look at familiar information. Another important implication of tracing Laniakea is the realization that observation is always limited by context. The universe we see today is shaped by the era in which we exist. We live at a time when stars still shine brightly, when galaxies are still visible across enormous distances, when superclusters can still be mapped. This will not always be the case. In the far future, cosmic expansion will hide distant structures beyond the observable horizon. The night sky will grow darker, large-scale structure will fade from view. Future observers may not be able to detect superclusters like Laniakea at all. This temporal limitation gives current cosmological knowledge special significance. It is capturing the universe in a particular phase of its evolution. It is preserving information that may become inaccessible later. Tracing Laniakea is therefore part of a broader effort to document cosmic history. It is a form of scientific preservation. Another implication concerns the relationship between humanity and the cosmos. As understanding of large-scale structure grows, the distinction between observer and observed becomes less pronounced. Humans are not outside the universe studying it from afar, they are embedded within it. Their existence is shaped by the same processes they seek to understand. This embedded perspective changes the nature of cosmic inquiry. It makes cosmology not just a study of distant objects, but a study of the environment in which humanity exists. Tracing Laniakea is therefore also a form of self-location. It is humanity mapping its place within the larger system. This act of self-location has deep philosophical resonance. It connects scientific knowledge with existential reflection. It encourages people to consider how local experience fits into a cosmic context. What problem? Another important consequence of tracing Laniakea is the demonstration of scale continuity. There is no sharp boundary between local and cosmic phenomena. Processes that operate on small scales often have analogues on large scales. Gravity binds atoms, planets, stars, galaxies, and superclusters. The same basic force manifests differently depending on scale, but the underlying principle remains the same. This continuity reinforces the idea that the universe is a unified system. It is not divided into separate realms governed by unrelated laws. Everything is part of the same physical framework. Laniakea exemplifies this unity. It shows how simple gravitational interactions accumulate into enormous structures over time. Another implication is the role of patience and persistence in scientific discovery. Mapping Laniakea required decades of incremental progress. Early galaxy catalogues laid the foundation. Later surveys improved distance measurements. Advances in computing enabled large-scale modelling. Only when all these pieces came together did the full structure become visible. This long timeline reflects the nature of scientific advancement. Breakthroughs often emerge from sustained effort rather than sudden inspiration. Tracing Laniakea is therefore also a story about perseverance. It demonstrates how collective effort across generations can reveal hidden aspects of reality. Another dimension of this discovery is its influence on future generations. Students who learn about Laniakea today may become the scientists who map even larger structures tomorrow. Public fascination with cosmic scale can inspire interest in science, engineering, and exploration. The story of Laniakea can motivate curiosity about the universe and humanity's place within it. This educational impact extends the significance of the discovery beyond academia, contributes to cultural understanding of science. Finally, tracing Laniakea brings attention back to one central theme: the universe is not static. It is evolving. Structures form, structures change, structures fade. The cosmic web itself is a dynamic entity. Laniakea exists as part of this ongoing transformation. It is shaped by past conditions. It influences present motion. It will evolve in the future. Understanding this dynamic nature helps avoid the misconception that the universe has a fixed architecture. It does not. It is constantly reshaping itself. This realization encourages humility in scientific interpretation. It reminds researchers that any cosmic map is provisional. It captures one moment in a long history. It invites continuous revision and refinement. Tracing Laniakea therefore represents both achievement and beginning. It marks a milestone in humanity's ability to map the universe, but it also opens new questions about structure, motion, and cosmic evolution. It shows how much has been learned and how much remains unknown. In the end, the true significance of Laniakea is not just its size or complexity, it is what it represents. A universe organized by simple laws, a cosmos shaped by invisible forces, a vast network of matter and motion connecting distant galaxies. And within that network, a small galaxy called the Milky Way, carrying a species capable of asking questions about the nature of existence itself. Tracing the edge of Laniakea is therefore not just an act of scientific mapping, It is an expression of humanity's desire to understand the universe it inhabits, a desire that continues to drive exploration, discovery, and wonder. And as long as that desire exists, there will always be new edges to trace, not only in space but in knowledge itself. As the full picture of Laniakea comes into focus, one final layer of understanding emerges: the realization that cosmic structure is not only a product of physical forces, but also a mirror of humanity's intellectual evolution. Every step taken to trace this immense supercluster reflects a deeper shift in how knowledge itself is built, tested, and expanded. Laniakea was not discovered by accident. It was revealed through a convergence of observation, theory, and computation. This convergence represents a defining characteristic of modern science. No single tool is sufficient. Telescopes provide data, physics provides laws, computers provide the ability to connect millions of points into coherent patterns. Together, they create insight. This collaborative process is itself a form of cosmic structure. Just as galaxies connect through filaments, scientific disciplines connect through shared questions and methods. Astronomy, mathematics, computer science, and physics form a network of knowledge that mirrors the interconnected nature of the universe they study. Tracing Laniakea demonstrates that understanding complexity requires systems of cooperation. No individual observer could perceive the structure directly. Only through shared effort does the larger pattern become visible. This has implications for how future discoveries will unfold. As cosmological datasets grow larger and more complex, the role of collaboration will only increase. Global networks of observatories, shared data repositories, and international research teams will become essential. The discovery of Laniakea is a preview of this future. It shows that the scale of questions humanity is now capable of asking requires equally large-scale cooperation. Another important realization that arises from tracing Laniakea is the role of uncertainty as a productive force. Scientific uncertainty is often misunderstood as weakness. In reality, it is a driving engine of discovery. Mapping Laniakea required dealing with incomplete data, measurement limitations, and model assumptions. Instead of halting progress, these uncertainties motivated refinement. New surveys were launched, new methods were developed, new models were tested. Each uncertainty became a target for improvement. This iterative process reflects the way scientific knowledge grows. It does not advance in perfect steps. It advances through approximation, correction, and revision. Laniakea's map will continue to evolve as new data becomes available. Boundaries may shift, flow patterns may become clearer, hidden structures may be revealed. This ongoing refinement is not a failure. It is the natural rhythm of scientific progress. Another dimension of tracing Laniakea is the shift in how humanity conceptualizes space itself. For much of history, space was imagined as an empty backdrop where objects exist. Modern cosmology has replaced this view with something far more dynamic. Space is not passive, it expands. It curves, it carries gravitational influence, it shapes motion. Laniakea exists not only because of matter, but because of the geometry of space-time itself. Expansion determines how far gravitational influence can reach. Curvature influences how matter flows. Dark energy modifies large-scale behavior. This means that tracing a supercluster is also tracing the structure of space-time. Laniakea is embedded within the fabric of expanding space. Its shape is influenced by the geometry of the universe. This connection between structure and space-time geometry highlights the deep unity between cosmology and relativity. It shows that large-scale structure is not separate from the nature of space itself. They are intertwined. Another important implication involves the concept of boundaries. Tracing Laniakea reveals that boundaries in the universe are rarely absolute. They are transitional. They are probabilistic. They are defined by gradients rather than edges. This challenges the human tendency to categorize reality into rigid compartments. The universe does not operate in discrete boxes. It operates through continuous change, gradual transitions. Overlapping influences. This realization encourages a more nuanced understanding of cosmic structure. It emphasizes that nature often resists simple classification. Complex systems rarely have sharp divisions. They exist along spectra. They overlap, they interact. Laniakea exemplifies this complexity. Its boundary is not a line. It is a region of shifting gravitational dominance. This complexity is not a problem to be eliminated. It is a feature to be understood. Another layer of meaning emerges when considering how tracing Laniakea influences long-term scientific goals. Future cosmology is increasingly focused on mapping the universe in greater detail. Projects aim to measure billions of galaxies, to track cosmic flows across larger volumes, to refine measurements of expansion and dark energy. Laniakea serves as a reference point for these efforts. It provides a local benchmark for large-scale structure. It offers a test case for new methods. It helps calibrate models. As observational reach expands, new superclusters may be mapped with similar precision. This will allow scientists to compare structures across different regions of the universe. They will study how environment influences cosmic architecture. They will test whether patterns observed in Laniakea are universal or region-specific. This comparative approach will deepen understanding of cosmic evolution. Another implication is the way Laniakea reshapes the narrative of cosmic history. Instead of viewing the universe as a sequence of isolated events, it becomes a continuous story of structure formation. From the early density fluctuations after the Big Bang to the present-day cosmic web, there is a direct evolutionary thread. Laniakea is part of this thread. It represents a mature stage of cosmic structure, not the beginning, not the end, but a moment in a long process. This historical perspective adds depth to cosmology. It shows that the universe has a developmental arc. It has phases, it has transitions, it has emergent complexity. Understanding Laniakea therefore contributes to understanding the broader timeline of cosmic evolution. Another dimension of tracing Laniakea is the shift in how scale is emotionally perceived. Numbers alone do not convey the immensity of the universe, but structure does. Seeing how galaxies cluster into filaments and superclusters creates a sense of spatial depth that raw distances cannot. It makes the universe feel tangible. It transforms abstraction into form. This emotional connection can deepen engagement with science. It can motivate learning. It can inspire creativity. Laniakea therefore has cultural impact beyond its scientific value. It shapes imagination. It influences art, philosophy, and storytelling. It becomes part of humanity's collective image of the universe. Another important implication is the reminder that discovery often changes the questions being asked. Before Laniakea, scientists focused on identifying clusters and mapping galaxy distributions. After Laniakea, attention shifted toward flow patterns, gravitational basins, and connectivity. This shift opened new research directions. It encouraged the development of new analytical tools. It changed how large-scale structure is conceptualized. This pattern will likely repeat. Future discoveries will reshape priorities and perspectives. They will redefine what is considered important. Laniakea is one example of how discovery transforms scientific focus. Another layer of meaning arises when considering the limits of observation. Even with modern technology, mapping the full cosmic web is impossible. The observable universe is finite. Beyond its horizon lies unobservable space. Within that horizon, detection becomes increasingly difficult at greater distances. This means that any map of cosmic structure is incomplete. Laniakea itself represents only one region within the observable universe. There are countless other superclusters beyond current mapping resolution. This limitation does not diminish the value of discovery. It contextualizes it. It reminds scientists that knowledge is partial. It encourages humility. It highlights the importance of continuous exploration. Another implication involves the relationship between theory and observation. Tracing Laniakea required theoretical models to interpret observational data. It also provided observational evidence that could validate or challenge those models. This feedback loop between theory and observation is central to scientific progress. Laniakea strengthened this loop. It tested predictions about cosmic flows. It refined understanding of gravitational structure. It provided real-world data to constrain simulations. This interaction between theory and observation will continue to shape cosmology. As new data becomes available, models will be updated. As models improve, they will guide new observations. This iterative process drives deeper understanding. Finally, tracing Laniakea highlights the human element of science. Behind every dataset are researchers who designed surveys. Behind every model are scientists who tested equations. Behind every visualization are teams who processed and interpreted information. This human effort is an essential part of discovery. It reflects creativity, persistence, and curiosity. Laniakea is not just a structure in space, it is also a product of human endeavor. It represents what can be achieved when knowledge, technology, and collaboration converge. As the journey of tracing Laniakea reaches its conceptual conclusion, one central theme remains clear. The universe is not static, it is structured. It is dynamic, it is interconnected, and humanity is not separate from this structure, it is embedded within it. Tracing the edge of Laniakea is therefore not only an exploration of distant galaxies, it is an exploration of humanity's place in the cosmos. It reveals that our location is not defined by centrality or isolation. It is defined by connection. Connection to gravity, connection to cosmic history, connection to the vast network of matter and motion that shapes the universe. And in recognizing this connection, humanity takes another step toward understanding the true scale of reality, not only in distance, but in meaning. Because the greatest discovery is not just how large the universe is, it is how deeply we are part of it. As the exploration of Laniakea approaches its final horizon, the focus naturally shifts from what has been discovered to what this discovery enables. Mapping a supercluster of this scale is not merely an endpoint, it is a foundation upon which future understanding of the universe will be built. Laniakea becomes a reference structure, a baseline for studying cosmic architecture, and a guidepost for the next generation of astronomical exploration. One of the most important consequences of tracing Laniakea is the refinement of large-scale cosmic cartography. For the first time, humanity has a detailed map of a gravitational basin defined not by appearance, but by motion. This introduces a new era of cosmic mapping, one where velocity fields and flow patterns become as important as spatial position. Future surveys will expand this approach. They will map galaxy flows across larger volumes of space. They will trace additional superclusters using similar methods. They will reveal new gravitational basins beyond Laniakea. This expansion will gradually produce a more complete map of the cosmic web, showing how superclusters connect and interact on the largest scales accessible to observation. As these maps grow in complexity, they will transform cosmology into a more dynamic science. Instead of static snapshots of galaxy distributions, scientists will work with evolving flow models that show how matter moves through space over time. This shift will deepen understanding of cosmic evolution. It will reveal how structures grow, merge, and dissolve. It will clarify the role of dark matter and dark energy in shaping large-scale patterns. Laniakea represents the beginning of this dynamic mapping era. Another important implication concerns the study of dark matter. Because Laniakea's structure is dominated by invisible mass, tracing its shape provides indirect information about dark matter distribution. Every flow pattern reflects gravitational influence. Every convergence point reveals hidden mass concentrations. As mapping techniques improve, scientists will be able to reconstruct dark matter structure with increasing precision. This will allow researchers to test competing theories about the nature of dark matter. Different models predict different clustering behaviors and filament structures. By comparing observations with simulations, scientists can narrow down the possible properties of dark matter particles. Laniakea thus becomes part of the broader effort to solve one of the most fundamental mysteries in physics. Another future application of Laniakea's mapping is the study of cosmic evolution across time. Although we observe the universe as it appears today, distant regions are seen as they existed billions of years ago due to the finite speed of light. By combining present-day flow maps with observations of distant galaxies, scientists can reconstruct how large-scale structure evolved over cosmic history. This time-layered view allows researchers to track the growth of superclusters. They can examine how filaments formed. They can study how voids expanded. They can identify when major gravitational basins emerged. Laniakea provides a local reference point for this historical reconstruction. It anchors the present-day structure within a broader evolutionary context. Another important direction involves understanding the limits of gravitational influence. Laniakea exists at a scale where gravity and cosmic expansion compete. Studying this balance provides insight into how far gravitational structures can extend. It helps determine the maximum size of coherent cosmic systems. It clarifies how dark energy influences large-scale structure. As expansion accelerates, superclusters will gradually lose coherence. Mapping this transition zone is essential for understanding the long-term fate of cosmic architecture. Laniakea offers a natural laboratory for studying this process. By observing how flow patterns change near its boundaries, scientists can measure the strength of gravitational binding relative to expansion. This information feeds directly into models of cosmic acceleration and the behavior of dark energy. Another important implication is the potential to discover new large-scale anomalies. Mapping flows across superclusters may reveal unexpected patterns, regions with unusual motion, areas with unexplained gravitational influence, structures that challenge current models. Such anomalies could point toward new physics. They could indicate variations in dark matter behavior. They could suggest modifications to gravity on large scales. They could reveal previously unknown cosmic structures. Laniakea's discovery itself was once unexpected. It is possible that future mapping efforts will uncover even more surprising features. This possibility highlights the exploratory nature of cosmology. Each new map is not just a refinement of existing knowledge, it is an opportunity for discovery. Another consequence of tracing Laniakea is its impact on how humanity conceptualizes cosmic navigation. Although intergalactic travel remains far beyond current technology, understanding large-scale structure provides a framework for thinking about cosmic orientation. It defines reference points, it establishes gravitational landmarks, it creates a sense of cosmic geography. Just as early explorers mapped continents and oceans, modern astronomers are mapping superclusters and filaments. This cosmic geography does not enable physical travel today, but it shapes how humanity imagines the universe. It creates a structured mental map of reality. This conceptual navigation is an important step in expanding cosmic awareness. Another important dimension is the integration of artificial intelligence and machine learning in future mapping efforts. The datasets required to trace large-scale structure are growing rapidly. Millions of galaxies, billions of data points, complex multi-dimensional measurements. Analyzing this information manually is impossible. Advanced algorithms will be needed to identify patterns, detect anomalies, and reconstruct flow fields. Laniakea's mapping represents an early example of this computational shift. Future discoveries will rely even more heavily on automated analysis. This integration of AI into cosmology will accelerate discovery. It will allow scientists to process larger datasets, It will reveal subtle patterns that might otherwise remain hidden. It will enable real-time analysis of new observations. This technological evolution will expand humanity's ability to understand the universe. Another implication of tracing Laniakea is the way it influences scientific storytelling. As cosmic maps become more detailed, the narrative of the universe becomes richer. Instead of a simple expansion story, the universe becomes a dynamic tapestry of flows, structures, and evolving patterns. This narrative complexity reflects the true nature of cosmic evolution. It moves beyond simplistic models. It embraces the richness of large-scale structure. Laniakea contributes to this narrative by adding a concrete example of how matter organizes itself on immense scales. It provides a story of gravitational basins, cosmic rivers, and invisible scaffolding. This story resonates with both scientific and public audiences. It makes cosmology more accessible and engaging. Another important aspect is the role of long-term observation. Mapping Laniakea is not a one-time achievement. It requires continuous monitoring. Galaxy velocities change slowly over time. Flow patterns evolve. New data refines existing models. Future generations of astronomers will build upon current maps. They will update them. They will extend them. They will improve their accuracy. This continuity of observation is essential for understanding dynamic cosmic processes. It emphasizes that cosmology is not static knowledge. It is an ongoing project. Laniakea is part of that project. Another implication involves the ethical dimension of scientific knowledge. As humanity gains a deeper understanding of the universe, it also gains a broader perspective on existence. This perspective can influence how societies think about responsibility, cooperation, and long-term planning. Understanding that Earth is a small part of a vast cosmic structure can encourage global thinking. It can promote a sense of shared destiny. It can reduce the emphasis on short-term conflicts and highlight long-term survival. While cosmology does not dictate ethics, it shapes worldview. Laniakea contributes to this worldview by reinforcing the idea that humanity exists within a much larger context. Another important consequence is the inspiration of future exploration. Large-scale cosmic mapping can motivate interest in science, engineering, and technology. Young researchers inspired by discoveries like Laniakea may become the scientists who map even larger structures. They may develop new tools. They may push observational boundaries. They may uncover new cosmic phenomena. This generational impact ensures that discovery continues. Laniakea becomes part of the chain of inspiration that drives scientific progress. Another dimension is the recognition that cosmic structure reflects both simplicity and complexity. At its core, Laniakea is governed by simple physical laws: gravity, expansion, conservation of energy. Yet the outcome of these simple rules is extraordinary complexity: filaments, voids, clusters, superclusters, flow networks. This duality between simplicity and complexity is a hallmark of natural systems. It shows how rich patterns can emerge from basic interactions. Tracing Laniakea provides a clear example of this principle in action. Finally, as the exploration of Laniakea reaches its ultimate perspective, one truth becomes clear. The universe is not just something to be observed. It is something to be understood as a system of motion, a system of connection, a system of evolving structure. Laniakea reveals that even the largest structures are part of this system. They are shaped by forces that operate everywhere. They evolve with time. They connect distant regions into a unified whole. Understanding this system does not make the universe feel smaller. It makes it feel more coherent, more meaningful, more comprehensible. Tracing the edge of Laniakea is therefore not only a scientific achievement, it is a step toward a deeper understanding of cosmic order. It shows that the universe is not random chaos, it is structured. It is dynamic, it is interconnected, and within this vast system, humanity has developed the ability to observe, map, and comprehend patterns far beyond everyday experience. This ability represents one of the most remarkable achievements of human thought. It shows that even in a universe measured in hundreds of millions of light years, understanding is possible. And as long as humanity continues to explore, question, and map the cosmos, structures like Laniakea will not mark the end of discovery, they will mark new beginnings. Tracing the edge of Laniakea ultimately brings the journey to its quiet conclusion, not with a final answer, but with a deeper awareness of how vast, structured, and interconnected the universe truly is. After following the formation of this immense supercluster, mapping its gravitational flows, exploring its boundaries, and understanding its place within the cosmic web, one truth remains clear: Laniakea is not just a structure in space. It is a window into the architecture of reality itself. When astronomers first realized that the Milky Way belongs to a supercluster spanning hundreds of millions of light years, it reshaped the meaning of cosmic location. The concept of where we are expanded beyond planets, stars, and galaxies. It now includes gravitational basins, flow networks, and cosmic environments that operate on scales far beyond direct perception. This expansion of perspective is one of science's most powerful outcomes. It allows humanity to step outside the limits of everyday experience and see the universe as a system rather than a collection of isolated objects. Laniakea shows that even the largest structures we can observe are not isolated islands. They are connected by filaments of matter shaped by invisible forces and embedded within a vast cosmic network. This understanding transforms the night sky. Stars no longer appear as distant, unrelated points of light. They become part of a grand pattern. Each galaxy belongs to a filament. Each filament feeds into clusters. Each cluster contributes to superclusters. And superclusters themselves are woven into the cosmic web. Laniakea is one thread in that web. Tracing it reveals how deeply organized the universe is, even on scales that once seemed chaotic. Another lasting lesson of Laniakea is the power of motion in defining structure. The supercluster was not identified by simply counting galaxies. It was revealed by studying how galaxies move, by following gravitational currents rather than static positions. Scientists uncovered a hidden layer of cosmic organization. This approach represents a shift in how structure is understood. It emphasizes dynamics over snapshots, processes over appearances, relationships over isolation. This dynamic view aligns with the deeper nature of the universe. Everything moves, everything evolves, everything participates in ongoing change. Laniakea exists not as a fixed object, but as a flowing pattern that reflects the balance between gravity and expansion. Understanding this flow-based structure opens new ways of interpreting cosmic evolution. It shows that the universe is not frozen in time. It is constantly reshaping itself. Superclusters grow, filaments stretch, voids expand, boundaries shift. This continuous transformation is not disorder, it is structured change. Another important realization from tracing Laniakea is the scale of cosmic humility it inspires. When the Milky Way is placed within a supercluster containing more than 100,000 galaxies, any sense of centrality disappears. There is no privileged location, no cosmic center, only networks of influence and motion. This perspective can be unsettling at first. It removes the idea that humanity occupies a special physical position in the universe, but it also offers a deeper kind of significance. Not significance through location, but significance through understanding. Humanity may not be at the center of the universe, but it is capable of comprehending structures that span hundreds of millions of light years. This intellectual achievement is extraordinary. It reflects the unique ability of the human mind to extend beyond immediate experience and grasp abstract cosmic patterns. Tracing Laniakea is a demonstration of this capacity. It shows that curiosity combined with science and technology can reveal hidden layers of reality. Another lesson lies in the role of time. Laniakea formed over billions of years. Its structure reflects the cumulative effects of gravity acting since the early universe. This deep time perspective challenges human notions of duration and permanence. What seems permanent on human timescales is temporary on cosmic scales. Superclusters will not last forever. Expansion will eventually weaken their gravitational connections. Structures will fragment. The cosmic web will thin. The universe will become more isolated. This future does not diminish the significance of present structure. It highlights the dynamic nature of cosmic history. Laniakea exists during a particular era, an era when large-scale structure is still visible and traceable. This makes the present moment scientifically special. We live at a time when the universe can still be mapped in detail, when distant galaxies are still observable, when cosmic flows can still be measured. Future observers may not have access to this information. This realization adds urgency to cosmological research. Mapping structures like Laniakea is not only about curiosity, it is about preserving knowledge of a universe that will one day become observationally inaccessible. Another important takeaway from tracing Laniakea is the interconnectedness of scientific disciplines. Understanding this supercluster required astronomy, physics, mathematics, computing, and data science. It required collaboration across institutions and countries. It required decades of cumulative research. This collaborative achievement mirrors the interconnectedness of the universe itself. Just as galaxies form networks, scientists form networks of knowledge. This parallel is not accidental. Complex problems require collective effort. Laniakea demonstrates what can be achieved when human knowledge operates as a network rather than in isolation. Another reflection arises from the emotional impact of cosmic scale. Learning about Laniakea often evokes awe. This feeling is not a distraction from science, it is part of the human response to discovering something larger than personal experience. Awe can inspire deeper interest. It can motivate learning. It can expand perspective. In this way, Laniakea does not only advance scientific understanding, it enriches human culture. It contributes to the shared sense of wonder that has driven exploration throughout history. From ancient star watchers to modern cosmologists, the desire to understand the sky has always been part of human identity. Laniakea is a continuation of this long tradition. It represents a modern chapter in humanity's effort to map the cosmos. Another profound insight from tracing Laniakea is the realization that the universe is both simple and complex. At its foundation, it is governed by simple laws. Gravity attracts mass. Space expands, energy is conserved. From these simple principles emerges extraordinary complexity, filaments stretching across millions of light years, clusters containing thousands of galaxies, superclusters forming vast gravitational basins. This emergence of complexity from simplicity is one of the most remarkable features of nature. Laniakea is a clear example of this principle. It shows how basic physical laws can produce intricate, large-scale patterns. This insight connects cosmology to other fields of science, from biology to chemistry to climate systems. Complex structures often arise from simple rules. The universe itself follows this pattern. Tracing Laniakea makes this principle visible on the largest possible scales. Another final reflection concerns the future of discovery. Laniakea is not the largest structure that will ever be found. As observational capabilities improve, new superclusters will be mapped. Larger structures may be discovered. New patterns may emerge. The cosmic web may reveal additional layers of organization. This means that the story of large-scale structure is not finished, it is ongoing. Each generation of scientists will build upon the discoveries of the previous one. Each new map will refine understanding. Each new insight will raise new questions. Tracing Laniakea is one step in this endless process of exploration. It is a milestone, not a conclusion. And perhaps the most important lesson of all is this: the universe is not something separate from humanity, it is the environment in which humanity exists. Every atom in the human body was forged in cosmic processes. Every molecule carries the history of stars. Every element reflects the evolution of galaxies. Understanding structures like Laniakea is therefore not only about distant space. It is about understanding the deeper context of existence itself. It is about recognizing that human life is part of a much larger cosmic story. Tracing the edge of Laniakea brings this story into focus. It shows that the Milky Way is not isolated. It is part of a vast network of matter and motion. It shows that the universe is structured, dynamic and interconnected. And it shows that humanity, despite occupying a small corner of this immense cosmos, has developed the ability to comprehend patterns that span hundreds of millions of light years. This ability is one of the most remarkable achievements of human thought. It represents the power of curiosity, the strength of collaboration, the impact of science. As the journey of tracing Laniakea comes to an end, what remains is not a boundary, but an invitation. An invitation to keep exploring, to keep mapping, to keep asking questions. Because beyond every edge lies another structure. Beyond every discovery lies another mystery. And as long as humanity continues to look upward and outward, the story of the universe will continue to unfold. One supercluster, one filament, one cosmic pattern at a time.